Wow! Hello everyone! So many friends today. So many good friends. Michelle, Reinhard, how are you doing? Nice look. And Antanas is there from Workstoff Photonics and Marilys from Rescoll. New friends. Benjamin, ¿cómo está? Buenas tardes. A great group of friends. Why don't we get the ball rolling? Welcome. Welcome everyone, ladies and gentlemen, to the epic online technology meeting on laser-based surface structuring. Today is a really cool day for many reasons. First one is for the Dutch people, Lars. It's King's Day. It's the birthday of the great king. Lars is celebrating with me about this. Also, we have a fantastic group of people from laser manufacturers with their optics all the way to users in different application fields. We have people from Fagor talking about the home appliance sector, or from Rescoll talking about the medical. It's going to be a great event. I have just a couple of quick things to share with you. The first one is I want to tell you that I am extremely happy. When Francesca and I had the idea of going online with this epic live, we didn't know it was going to be so successful. We thought it was going to be a nice idea, few people, but we are getting so many requests from people to participate, such great or positive feedback. So in the beginning, we came up with these fantastic 15 topics, and I can already tell you that this is not going to end, or we already have even 16 more topics to announce after these ones. So we already have meetings planned all the way to 22nd of June 2020, and confidentially, nobody's listening. I can already tell you that we're going to continue after this. This is the new life. This is the online life. This is the new world in which you have to live. I am really so happy that this online concept is flying. Also, I would like to tell you that thanks for the support, the 550 members of EPIC keep giving us. We are managing to do great things, and we want to continue growing. So for those of you who are not yet member of EPIC and you want to consider the possibility of getting access to the market reports or the coming to the meetings, please join us on this live that Francesca and me are living. Many of you know that the online world is nice, but eventually the virus thing is going to be over. I hope soon. I really hope soon. And we also will continue with our present meetings. And I can already tell you that we have great meetings planned already for the end of this year and next year. I would like to bring your attention to the EPIC meeting on industrial lasers that we're going to have in Torino at Convergent, at the headquarters of Prima Electro Group, focusing on different metallurgic assemblies. And many of you have seen the market report that Carlos Lee announced last weekend on LinkedIn. We're getting a lot of views on this. We managed to purchase what we think is the best laser market report that there is available from Strategies Unlimited. So all of you EPIC members have access to it. I spent quite many hours during the weekend. My wife is not happy. I spent a lot of hours during the weekend trying to read it, and there is a lot of information. I was quite amazed on the growth, for example, femtosecond lasers on the semicon market. It is something worth it reading. So for those of you EPIC members, this is already available for you. Have a look at it. We are extremely happy that we managed to buy it. It wasn't cheap, so use it, abuse it, try to get the most out of it. And also we can tell you that we are also extremely happy with our activity, jobsinphotonics.com. This is already the largest photonics job hunting website in the world. We are scouting the job openings of the 550 members of EPIC. We are selling this, we're giving this to the different companies, recruiting talent, as well as the people looking for a job in photonics. And this is what we have today. This is the agenda. The agenda starts with a company that I am really fond of, and I will introduce later, and it goes to the entire value chain. When I see it like this, I find it very exciting, but when I see it like this is when I really like it. And especially when my friend Francesca presents it, it's when I love it. Francesca, che cosa mangiamo?
Cosa mangiamo oggi? So that's the menu for today. Thank you, Jose, for giving me the word. So as we said, I mean, surface structuring, everybody thinks, what does can mean, or what is it exactly about? But we know that this, after this talk, if you didn't know what it is, you will know it will be really useful, because look at how many end users we have that can actually use it in their in their activities. So for medical application, you need to functionalize surfaces, but it can be also for semiconductor technology, for lithium batteries to improve the functioning, for home appliances. So we will understand how this is useful for these end users later on, but also we will see how this is allowed. So we will need, of course, laser to do it, because this is basically what we will talk about today, is more a laser-based structuring activity. We will have a lot of people talking about the laser system. We will have a lot of people talking about the integration. So how to integrate a system that they can actually very efficiently produce this surface structuring on the surface of our utilities. And then we need, of course, the beam shaping. So we have also speaker from, for example, Kylabs and PLX, but also inspection, because you wanted to check what is going on online. And so that's why we have, for example, new infrared technologies, or RIBA, and also we have actually a hyperspectral imaging European project that can deal with this inspection of these activities. And also, of course, laser optics. So we have, for example, a Sphericon today, and a polygon scanner from Nescan Technology, very important. So we want to be fast and effective, so we need polygon scanners. And then components, for example, PI, Velo, Hamamatsu. So we have really a wide group of users, and so the full value chain is there, end users, manufacturing, and so this is exactly what we want to have today. And then one thing that is also important, and if Jose goes further, thank you. So this is basically an idea that, so this functionalization of surfaces is clearly important, because there are many European funded activities about it. And one of them is called LAMPAS. And basically LAMPAS is a project that is dealing with creating a system that can deliver high throughput and low cost production of functionalized surfaces with micro and nanometer size topographical features. So the applications we will hear later on will be, for example, anti-fingerprint. So the surface can stay clean or is easy to clean. There are antibacterial properties, so that's why also for medical application is really important. You can also make decorative finishes, and really many more possibility that is better if the people and the main actors will describe you later. But what LAMPAS actually is focusing on, and is the method, how to get to this very efficient functionalization of surfaces. And this can happen if you use a strategy called direct laser interference patterning. And basically is inspired by nature. So we want to define on a surface these nano and micrometer size structures with the laser and with special interference patterning. And to do this, you need for sure a laser, and then you need the scanners, and then you will need also monitoring of this. So this will be the main partners in LAMPAS. Then, of course, this is not easy. Otherwise, we would have already done it long ago. So there are targets and challenges, of course, in this project, and also other European activities that are focusing on how do we reach this resolution. So the resolution is we want to be on the hundreds of nanometers, but up to 30 micrometers. And so this is possible only with a special achievement that you can get with direct laser interference patterning on a 3-level hierarchical pattern. Basically, you can cross basically the beams, as you see in this image close by. And if you have the right parameters, basically you can reach structures that are on the micrometer scale, but even on a lower scale, you can basically induce a periodic surface structure called LEAPS that even reaches the lower scale, because it's dependent, of course, on the wavelength of the laser you're using to generate it, and on the angle of your multi-beam that you are using. So unfortunately, the thing that is making it this really a challenge is the throughput, because this is possible, of course, in your lab if you're a scientist, but then you cannot sell it as a tool. So to sell it as a tool, the target of LAMPAS is to reach up to 1 or 5 square meters per minute. So you want really to cover a surface so fast that is actually efficient for a company, for an end user to have such a machine. And for this, we have lasers, so that we will use. So it's actually Trumpf in our partnership that uses picoseconds laser at 1 micron with a power of roughly a bit more of 1 kilowatt and a repetition rate of megahertz. But the deal is to reach actually a scan speed that is 100 meters per second. And so we will see later Lars talking about it probably, where are the challenges in being so fast but still be in high resolution. And then, of course, the complexity, because to get this setup then all together that is actually efficient, that is fully automatized, that is an online controlling, and so an online camera on it, and controlling all the multi-beam system to be actually efficient in the resolution, you have then to have the issue of get the system integration. But this we will hear also later on from other experiences, Lampa's experiences, and we will hear how fantastic can it be to have such a device, a complete device. And now I maybe leave the word to Jose, and we go really into the rocking.
From EPIC, we really appreciate the support of Photonics 21 and the Photonics PPP, who make to a large extent having the entry point to new innovation technology. So thank you, Photonics 21, and thank you, the Photonics PPP. I would like to give a fast final message to everyone, not only here in the participant Zoom channel, but also in the YouTube universe. We have a lot of viewers in YouTube. I would like to let you know that if you want to contact any of the participants today, you can just simply send me an email, jose.pozo@epic-aso.com, with the participant that you want to be introduced to. And it is our duty or job, but also our pleasure to introduce all the speakers to the potential partners, suppliers, customers, or even future friends. So please, an email, jose.pozo@epic-aso.com, if you want to contact any of the speakers. And now let's give the floor to the people who made a difference in the world industry. Microrelleus, EPIC member for already almost 2 years, is the entry point of the surface structuring at EPIC. Raúl, thank you very much for being with us this afternoon. Tell us how the community can benefit by Microrelleus technology.
Thank you very much, Jose and Francesca. I think you can see my screen, right?
Very clear, crystal clear.
Okay, great. So I am Raúl García from the company Microrelleus. I will speak today about the industrialization of functional texturing for different applications using a femtosecond laser service in 5-axis. Okay, I will speak just 1 minute about who we are, then small time also about the femtosecond laser technology for the ones that doesn't know. And then we're going to explain several examples on functional texturing and microstructuring using this technology, okay? So that's our company. We are a service provider for industry. What we do is laser micromilling, laser texturing, and microstructuring and industrial engraving since 1983. We are based in Barcelona, and in 2013 we were the first company in Spain and Portugal offering nanosecond laser in 5-axis service, and in 2016 pioneers offering femtosecond laser service in real 5-axis. So for the ones that doesn't know what a femtosecond laser is, the main advantages or differences or benefits against other fast lasers like the nanosecond laser is that thanks to this ultra short pulse duration laser, we are able to achieve an ablation, a micromilling, a microstructuring without almost thermal affection over the part. So we can achieve absolutely burr-free microstructuring or micromilling. So compared with conventional technologies, we can achieve very small details without absolutely burr-free and very clean results. So about machining technology positioning, it is between nanotechnology and the size that we can achieve using conventional technologies. So we work sometimes, as I spoke before, we are a service company. We work sometimes for a mold and sometimes on final part, and we are going to see now some examples here. The first one is the capacity to obtain hydrophobic textures. What we do is we texturize the mold, plastic is injected, plastic replicates the microstructure of the mold, and we can see this hydrophobic property in the plastic part. We can see here the difference of behavior and area of the plastic part which was texturized and the one that was not texturized from the mold in this case. In this case here, we can see some sensitive texturing. We can achieve pitch skin effect, the velvet effect in plastic part, as far as we inject a flexible plastic in a mold. We can achieve as well soft touch effect, anti-scratch effect as well. And speaking about design, we can see here an example combining different textures with the light diffraction texture that we can obtain using the femtosecond laser. And again, worked on the mold and plastic injected in this mold, and we can see the colors because of this light diffraction texture in the plastic part as well. We can see here a small video of the mold and small video of the plastic part as well, where we can see all the colors and effects in the plastic part. If we split directly working over tool or over part, self-lubricating these small holes that keep the oil here for different tooling. Also integration textures to improve the osseointegration in spin plates, hip joint, dental implants with some benefits against the conventional techniques. About lighting, we are working a lot. In this case, is the explanation about prototypes. In this image, we can see some standard roughness that we can find in the market, but we're not able to apply in the prototype, so directly on PC or PMMA, okay, which are the VDI that we can see in the left-hand side. So we are able to apply this roughness, which are standard with some values of RA, SA, etc., in the prototype. So our customer is able to do photometrical analysis of the prototypes, not need of doing the mold. Or on the right-hand side, this microstructuring for the light curtain in the three rear light of the Cupra Tabascan presented in Frankfurt last year. About microstructuring of molds for lighting industry, the same. We can achieve very small details with very, very small radius. So for optical designers, optical engineers, there's a new limit in the possibility of designing. And for texturing, again, we can achieve homogeneous light diffusion, controlled light diffusion, that can be an alternative of the standard materials used in industry, just because of the fact of using this technology, this femtosecond laser technology, to work over the molds for this lighting industry. So it was a small overview about some projects we have done in functional microstructuring and texturing. Sometimes, as we saw, we work on the tools. Sometimes in the final part, we do a lot of R&D for customers as well, because there are a lot of new things that we can do thanks to this technology. Sometimes we need the help of technology centers, universities, etc., that help us to develop a texture that we are going to industrialize in the part or in the tool. Okay, our customers are final product manufacturers, mold makers, plastic injectors, OEM, tier 1, tier 2, of a lot of different businesses, as you saw before. So it was everything I wanted to explain in these 6 minutes. So I don't know if someone has some doubts or something that want to comment to me.
Yes, thank you very much, Raúl, for your contribution. So, as you probably already know, you told us one side of the question, so what you can do for this audience. But maybe you can specify a bit what the audience can do for you. So remember how many people, if you don't recognize all of them, there is the full value chain here. So any wish that you have, you can express it here, and maybe by the end of the meeting, we have already a couple of collaborations about it.
But sometimes people doesn't know that it could be some good functionality for them. For example, we have worked a lot for electrical appliance, for automotive industry, for aerospace as well. But a lot of times people from these industries, they don't know how we could help them on different functional texturing, because they don't know the technology, or finally it's something about thinking on how could we improve their product or achieve something that was not possible before for them, just because of this modification of the topography of the part or of the infill without adding any extra material or chemicals or something, no? So finally, it's about thinking how microstructure or functional texture could improve their project, their product, and ask us for some idea. Or we have seen a lot of different projects So maybe we could help not just in the realization, but also to find ideas for that.
So I have a question.
Yes.
Whether it is dependent on material like silicon carbide, tungsten carbide, and silicon nitride, whether these three materials are user friendly for laser structuring for dirt free or water repellent?
Well, thank you for your question. Well, for the moment, we never found a material which is not able to work with the femtosecond laser, at least our laser machine laser source. Okay, but of course, the behavior of the laser is not exactly the same in the different materials. For example, in steel, we can work with higher quality than in aluminum, for example, or in glass. So I would say we can engrave almost all the materials, but not with the same quality. So it depends on the requirements on each project.
Okay, what is the roughness you achieved using your service?
The roughness, we can arrive, depends on the material and in the structure, but until 50 nanometers, for example, we have done projects. But if you need a roughness better than this, very, very difficult. I would say at least we can't achieve it. We need some post-process after the laser engraving or microstructuring.
Okay, thank you.
I don't want to.
Yeah.
Yes, I don't want to be negative, but the thing is, these surface structures exist since a long time. Last year there was a big hype on very large diffusion angles, and the problem was Rochester Photonics. It has patents. They got bought by Viavi, and these patents covered all these big diffusers that industry wanted to have. So I see it's interesting what you're doing, but the bottleneck is not to create the structures. You can get all these kind of structures, many different technologies. The problem is, are you allowed to use it, yes or not? And for applications in smartphones and where the big money is, there are patents which will block absolutely every business that you could find. That's maybe negative, but this is how I see the world today, 2020.
Okay, if I understood properly, you were speaking about structuring for lighting in smartphones and tablets?
Okay, so let's keep it like this. Using very small, random, whatever structures just to create an image or create something. This is a very old hologram technology 30, 40 years ago, okay? So you have all these tags, you have all this, these structures exist since ever. There are two bottlenecks. The one is make it cheap, and the other one was big angles. Getting the light on big angles, and the application is very clear. You want to distribute the light over a very large angular field for LiDAR, for all this. And there are patents by Rochester Photonics, which have been bought by Viavi, and they are blocking the whole business. Everybody wanted to buy from us replicated diffusers. It all ended up, you're not allowed to use these nano structures because the patents block everything. Maybe somebody has a different point of view, but this is why I don't see that you will find any business for these structures.
Well, maybe in specific markets, but for the moment, at least with our customers, we never found a problem like this, or at least in most of the cases. But maybe we can speak later personally and speak about.
No, there's no problem. That's okay. It's just if you get into real business, if you get out from prototyping, you might run into severe patent issues.
Sure. Yes.
Is there someone else who can maybe?
I have a question.
Yes.
Hello.
Sure. Hi, our semiconductor guy.
Yeah.
Thank you, Ben.
So first of all, thanks Raúl for the nice overview. And I was playing around some years with hydrophobic and hydrophilic surfaces, and I was wondering, are they now stable? Because I think they was very sensitive just by touching it or putting a little bit sweat or whatever. Maybe you can tell us a little bit about that, how sensitive they are and how we can use them. Thank you.
Yes, thank you very much, Benjamin. Yes, they are absolutely very sensitive to the human finger, for example. So we just recommend them in protected environments. And as it is something very new as well, until there is no real production on the market, you can't be absolutely sure how long will be okay the texture over the part and so on. In specific hydrophobicity, all the projects that we have done were for R&D for customer. So it's customer that subcontract us. We apply the texturing in their molds, they inject, they do all the tests. And for the moment, it's everything we have done. Several shapes, flat, 3D shape, and so on. But yes, for the moment, not serial production. But of course, we know this is an important issue here for this structure. Absolutely.
And one last question, how reproducible are these kind of structures? For example, if I have, let's say, a 300 millimeter wafer and I have idea of structuring somehow, and how reproducible is this? How stable I can get, let's say, 10,000 lines on my wafer? Just random question. So it, of course, depends a little bit on the application, but yeah, assuming nice scribe that you showed on, I don't know, one of your last slides, just to get a feeling.
Okay, you mean when we create the microstructuring, or when the plastic is injected in the mold?
No, when you create a microstructure, how reproducible is this? I mean, how is this? Are there big deviations from, let's say, you do it on day one and day two? I mean, how?
The deviations we can find, at least for the moment, we're not sensitive for the functionality. Finally, what we do is we create the texture in an area. Okay, we take a confocal microscope, we analyze the different areas, and if the usually it's the same, the engraving in all the areas. So we never found problems because of that. Of course, we have to take into consideration the parameters of the machine, which are difficult to reach for each material. But once you have stable parameter, we never found important deviations in terms of repetibility.
So great to have the end users today. Benjamin, thank you very much for contacting in LinkedIn and now following up here. He said, do you want to have an end user in the semicon market? That's what he asked me in LinkedIn. That was great. Microrelleus, we have a question from the YouTube universe. One of the venture partners, Evolve Strategic Ventures, is wondering, Lin Shihan is wondering, what is the largest surface you can process?
Okay, our machine that I mentioned, the X and Y mechanical movement, is 600 per 400. Okay, we can put bigger parts, but if we want to engrave everything continuous, like in the same fixture in the machine, it will be 600 per 400.
Excellent. I want to revisit the IP issue, but I want to do it later, much later, after José Luis de la Peña's presentation from Fagor. I think I want to go back to that topic when we have all the end users presenting. But until then, Raúl, thank you very much. Muchas gracias. Fantastic presentation. We move to the next speaker today. We go to Rescoll. We go to the medical market. Marilys Blanchy is her first ever EPIC meeting. So please be nice to her. She's going to tell us what we can do for Rescoll. Thank you very much for being with us today. The floor is yours.
Thank you for the invitation. So I will try to share the screen. So I hope you all see my screen and this is okay.
Yes, perfect.
Yeah, so first of all, thank you for the invitation. So once again, this is my first time in EPIC meeting. I'm sure that will be very interesting and very fruitful in terms of discussions and knowledge we can learn on the surface structuring. So today I will focus on the interest of using surface texturations for medical application, and especially a laser texturation for osseointegration. So a few words on Rescoll. So Rescoll is a French company. It's a group of services companies specialized in polymeric materials, in bonding assemblies, and in smart surface. Our main activities in aeronautics, medicals, and energy. We provide three kinds of services. So first of all is a chemical mechanical surface characterization for on routine in the frame of research and development for our customers. Our second activity is more about research and developments for innovative materials and surfaces. So part of the research and development teams, we are involved in several European projects. And my aim today is to present you the result obtained in the frame of one of them. The project is called Laser for Surf. So Laser for Surf project, as I said, is a European project and is composed of 8 different partners, several technological centers, several companies, and 3 end users, so Fago, Rescoll, and CC Energigune. So I will present first the project and then the result obtained for medical application. And then Fago and CC Energigune will present their own hand use case. So as I said, the objective of the project is the development of a laser texturation on metallic surface for 3 use cases, so medical implants, battery, and linear encoders. So the objective of the project is to obtain all-in-one machines comprising a laser texturing devices, an inline monitoring systems, and a simulation tools. So applying a specific type of patterns and roughness is using laser technology have significant commercial potentials. It allows improvement of product performance without altering surface compositions or adding any coating. So especially femto laser lips, allowing cost-effective process times. And today, as I said, I will present you the interest in applying laser texturation for medical implants. So first of all, what is interesting for medical devices to use control of the surface is because there is a failure of implantation time to time due to the wrong integration of the implants. It's what we call osteointegrations. One of the most used materials today for orthopedics, for example, or for digital implant is titanium. So it's a very well-known and extremely biocompatible materials. And it has excellent corrosion resistance and good mechanical properties, but it also quite innate towards cell interactions. So in some cases, implant shows long-term failures due to insufficient integration toward bones. So several studies showed that good interactions can be improved by modification of the surface of the implants. So it can be either chemical modification or physical chemical modifications. So we can see here, so there is 3 scales in the topography to improve the relationships and the interaction between cells and in between the devices. So first of all, there is what we call the macro topographic features. So there's a bigger size features, which is dependent of the design of the implants. The micro topographic features here, so it's responsible for mechanical anchorage of the implants towards the bone and improving the bone to implant interactions and contact. And the last thing is to have a nanotopographic features that will interact with osteoblasts directly. So there will be cell recognitions and cell proliferation toward the surface of the implants. So nowadays there are several methods used, as I said. So they use chemical surface modifications such as acid etching, anodizations, or chemical coating. Or there will be physical and modifications such as sand or grease blasting. The main limitations of this currently used methods are, first of all, they use harsh solvents. They are not very controlled in terms of the topography and the features. So it's aleatoire features on the surface. We cannot have a control directions such an anisotropy of the features on the surface. And finally, it changed the chemistry on the surface of the implant. And in terms of regulatory standpoint, it's sometimes difficult to be approved. So in that context, femtolaser texturing seems to be a good alternative route because it does not imply any chemicals, or it do not produce dust or particles during the processes. So this is the objective of the Laser First project, is to demonstrate and to validate the use of laser texturation technology on metallic surfaces for better osseointegration. So first of all, if we are thinking of the specifications of medical applications, so what are needed to have a good technology to be used in medical devices? So first of all is to improve the osseointegration with topographic features, to be clean and environmentally friendly materials, to be fast and cost effective. For sure, if it's like much more expensive than already used technology for functionalization of the surface, it will not be worth it to go with such a technology, to meet regulatory standards and to be applicable both on small and complex shaped surfaces. So here I just want to show you very quickly a few results we have. So we can see here in the framework of the development project, we managed to obtain quite controlled surface with a good anisotropy and very well oriented surface. We can see that the surface is homogeneous and have nicely distributed features on the whole surface of the titanium specimen. We can see here that the periodic features is well controlled and well reproducible, and then we can control the pattern obtained by fine-tuning the process parameters. So in terms of functionalizations towards cell applications, so here we just saw the functionalization of cells. So there are three parts in a good osseointegration: cell adhesion, cell proliferation, and cell functionalization. So we can see here that we can improve by twice the mineralizations of the surface, which is meaning that functionalization is much better with laser-induced surface texturation. So this is like a good proof of concept. And finally, we also worked on 3D shape product. So here, this is a screw, for example. So we can see here that we were able to functionalize and to have a specific area of the texturations, and so that means that we can fine-tune the texturation on the surface of the implants. So to conclude, the laser texturation is a very promising method for surface treatment to obtain fine-tuned surface parameters according to the specification we wanted to reach, to treat complex surface and to have no chemical modifications of the surface. So I would like to thank you for your attention, and this is an acknowledgement on the project, and I don't know if you have any question.
Thank you very much, Marilys, for your contribution. So it's clear that they have already good results. Maybe they can get better. Maybe they have some other questions or some issues. So do you have a direct question already to ask, Marilys?
Yes.
I see Tim. You can ask the question.
Okay. Marilys, very nice presentation. Just one question concerning, so it's obviously it's a dental implant. And actually, what is the goal? Is there a target process speed which you would like to achieve at the very end of the project? Or maybe it's already...
Is the speed, you mean the speed of the process, right? I understand.
Yeah, exactly.
Yes. Yeah, it's like we were reaching like a few seconds per product. So we are working also with laser, which is part of the consortiums to have like a good process, a continuous process to have like the best productivity. So it's all depending of the size of the screw and the way we are. We will be able to treat several screws actually. So today says for sure that the interest today it's that it will be a one-step process. And nowadays we will have several step process because the conventional methods are producing leachables, so that need a cleaning steps behind the surface functionalization. So for sure that will be interest in using laser treatment just for that reason already.
Thank you.
So are there other questions now? Because you clearly already asked, so Tim already asked you, one of your challenges then the throughput, right? So you have to be, so Lazia managed already to help you in getting, so you said a few seconds per product. So this is a bit of a challenge because you probably want the best, so the faster the better, I assume.
Yeah, sure.
Nah? So do you have otherwise other challenges that you would like to optimize the system? So of course, cheap, I assume, but maybe you have other instances that maybe someone can help you with.
Yeah, the main challenging, as I said, in the project is to have like a fast, but also a clean process, have an inline monitoring systems that will also be part of the project, Laser for Surf. So there will be there is a website on Laser for Surf project. So if you want to see, I put the link on the last slide of my presentation. You can have a look on it. But the inline monitoring systems and the inspections, it will be something that will be very interesting in the project. Yeah, eventually it's just to catch up with all the kind of application. For sure, I think it will be interesting to diversify the potential also of the laser in high added value application.
Okay, that's a good overview. Then there's Sabrina who wants to ask a question, please. You have to unmute yourself. Yeah.
It's not that I want to ask a question, but in terms of increasing the efficiency, it's maybe we have something that could help. And if you like, Marilys, I could send you a publication that we have, a paper that we have published last year. And it's about how we could improve the efficiency by using some beam shaping methods in those lips, especially in those surface structuring.
Yes, of course, that would be interesting. So yeah, send me the publication for sure.
Mm-hmm.
That could be great. Yeah. Thank you.
I guess, can you maybe explain, is it something with transmissive optics? Is it the thing I have in mind,
yes,
Sabrina?
It's,
okay, you can describe
it's one
it
of our beam shaping. It's one of our beam shaping products, and it's a refractive element, so it's all transmissive. You don't have any losses, and you can use it in a very broad band of wavelengths. So it might be something that can be very useful for the applications you have, because it's not only good for, let's say, the one wavelength, and then you need something for the other one, so you can use it in a broad band. So maybe it can help. Let's just see. I sent you some information on that.
Yeah, sure. That would be interesting to have a look anyway, and to compare with what we are doing in the project, because as I said, there is also already some inline monitoring systems that is forecasting the projects by other partners. And
I know that Tim from Fraunhofer IWS, I think he's in good contact with with our head of applications, who is kind of designing the latest version of it. So I think he knows what I'm talking about.
Yeah, it's true.
It's so great to have you here, Sabrina. If you guys have time later after the meeting, we have one question from Nahem. Yes.
Yeah. Apart from dental, first, thank you for the presentation. Apart from dental, do you have any specific application in other medical devices like stent devices or any other components?
Yeah, mainly for every bone applications, like in orthopedic, for example, that would be quite interesting. Also to have surface texturation, as long as it's relating to improving the bone to implant contact, that could be interesting.
Okay, thank you. Yeah, that's it.
Yes, I was saying it's great to have Sabrina in the audience. If you have time, go to check her YouTube videos. They're spectacular. But I have two questions, very quick questions. One is back to Rescoll. I get Antonio Raspa from Quanta asking, is the process made under inert gas or in air?
No, the process is made in air.
Okay, and then I have another quick question that I received by email. And that question is from Kinegram. The head of optical technology, Hannah Walter, is asking Raúl from Microrelleus. Raúl, what is the lower limit for the structure size, which can be done with your technology?
Yeah, actually...
the question was for Raúl from Microrelleus. Sorry, Marilys.
Yeah, for Raúl, the question, so let him answering maybe the question.
Can you repeat, Jose, please, because you asked that the lower remove material?
The lower limit for the structure size.
The lower limit for structure size. Ah, okay, my laser spot diameter, I assume?
Yeah.
Okay, usually we are using 50 micron diameter. We change length and can arrive until 15 micron. Okay, so we really can have until 10 more or less. 10, 15 micron.
Is there any other question from the audience? If not, we need to move on and go to the next speaker today. We go to the beautiful world of lithium batteries. I have the honor to have the next user, CIC Energigune, Miguel Angel Munoz. Thank you very much for being with us this beautiful afternoon. How is the weather over there?
Jose, the weather is as usual, a bit rainy with some sun, so it's fine.
It is great. Yesterday, the children could get out in Spain for the first time after some time. People are really happy, great mood. The floor and the attention of everyone is yours.
Okay, thank you very much for this opportunity to present more of the laser for Scharf work. Let me, if I can. Yes, I think. Are you seeing the presentation now?
Yep.
Good. Perfect. So, well, first of all, thank you for this opportunity. Also to Marilys for having this such a nice overview of the laser for Scharf project. So I can save that and then move on directly into the concept and results of applying this laser processing into the lithium-ion battery world. Of course, this is a project that is coordinated by CEIT. I guess Ainara is the coordinator. Ainara Rodriguez, she is in the audience, so she can give us a hand also if needed. Well, as for CIC Energigune role, we are a research center working on energy storage mainly, so electric energy storage or thermal energy storage. This application of the laser for Scharf was foreseen for lithium-ion batteries. So first, I would like to start with how a lithium-ion battery works. So essentially, you see here a picture in which you have on the left-hand side the anode, the negative electrode, which is attached, is a material, typically graphite in most of the commercial batteries, which is attached to a copper current collector. And on the other side of the battery, we have the cathode, the positive electrode. There is a series of interesting materials commercially available to produce these batteries. In this case, we use an aluminum current collector. And in between, we have a separator, which is not plotted in this diagram, is a typically glass fiber or polypropylene separator that is placed in between the two electrodes, so they are not in contact. Otherwise, you will have a short circuit. And then we have this separator is soaked with a liquid electrolyte. Then during the charge of the battery, the lithium ions, they move towards the anode, towards the left-hand side. Then the electrons, they go on the external circuit. And during the discharge, is opposite way around. It's a rocking chair concept. So the lithium ions, they go into the cathode, and the electrons following the external circuit will power our device. So why is laser an interesting laser structuring, an interesting application for lithium-ion batteries? So if you see in this diagram, we have a current collector. The contact in any of the electrodes with the anode or the cathode is done through a casting. So essentially, you take a copper foil in a production line or an aluminum foil, and you cast the electrode as a paint, and then you dry it, and finally you assemble the battery. So electrons, they have to go through the current collector towards the anode or the cathode. So that interface is crucial here. Then we came with the concept of what about if we structure the surface of the current collector, and then we allow for a bigger surface area that will have a twofold effect. On one side, you will allow for more electron transfer. So you can, this is translated in being able to operate the battery at a higher current, so faster charge or faster discharge when needed, so more power. And also it would impact on the addition of the electrode to the current collector. Then, as I was saying, we were using the current collectors processed by our colleagues in Theid with LIPS. And our idea was first to have a kind of test on trying with the different laser parameters, working on small coin cells, the ones that you have in your watch or so on, and essentially that have a small area of 1 square centimeter, more or less, and then also have like a prototype concept of a pouch cell, which in our case has the size of a battery that you can find in mobile devices, mobile phones, for instance. So like a proof of concept that this can be done in a larger area. And essentially this is like a 4 by 6 centimeters area. So we got very interesting results from the last part. I mean, we got very good results on the coin cell, but also on the pouch cell, and this is what I show here. With this structuring, as I was saying, we managed first to increase to improve the stability of the battery. So if you see on the left-hand side, you will see a green line, which is, let's say, the capacity of the battery as you cycle in a total of 100 cycles. The green one corresponds to a bare copper current collector, and the purple one corresponds to a copper structure current collector. So you can see, although you have a small drop in the capacity, then the stability, so the capacity remains constant with the cycles, whereas in the bare copper it drops. So we prove here that was very interesting, this structuring for the stability. We also notice that the capacity retention, this is the capacity that the battery can give you, can release, compare with the initial capacity value, is 99% in the case of structured copper and 90% in the case of conventional copper current collector. And finally, also very, very interesting result that we obtained here with this processing was testing how the capacity of the battery is affected when you charge or discharge at a very high speed. So essentially, if you see on the right-hand side, 0.1, 0.2, 0.5, C, this is the charge discharge rate. 0.1 means charging or discharging in 1 hour, in 10 hours, sorry. Whereas 1C is charging or discharging in 1 hour, and 2C is in half an hour. What we see here is that we improve the capacity of the battery, has a much better capacity when you structure the the current collector. So essentially, you improve by 16% at 1C and 61% at 2C. Being this point very, very important for a high power application that allows you to operate the battery very, very fast. So these two are the main results that we obtain for the batteries. That they are is a very good, very high impact results. I would like to finalize with by acknowledging all the financial support obtained by the European Commission through the Laser Forcer project, and also all the people that has been working on this on both institutions, CIC, Energigune, and Untitled. And now I'm free and open for any question that you may have. Thank you very much.
Thank you very much for your contribution. So I would say is the same technology. So just to remind, is the same technology that also Marilys was mentioning before, applied just to another end case. So I can maybe ask you as well the same question that I asked to her. So what about the throughput? So is it a challenge to be fast in microstructuring your batteries? Is it still an open question, or how is it the situation?
Well, our main concern at the beginning was to be able to structure a large surface, and we managed to do this. I mean, Said managed to do this in a 5 by 6 centimeter area. Now, this is proving the concept that we can go bigger. Ideally, and that depends on the application. If you stay in like mobile phone applications or smaller batteries, this is okay. Then if you want to go to like cells that you implement in a car battery, for example, then you need bigger areas. Let's say like A4, like a paper, right? 20 by 20, something like that. In this case, I guess it's just a question of working on the engineering of the laser process. And regarding the speed, at some point, if you want to meet the speed of production of batteries, this is about between 10 and 20 meters per minute. And probably there we have to work more.
Okay, so you mean to reach 10-20 meters per minute is still an open question. So maybe,
yes.
Okay,
yes.
okay. So maybe someone wants to comment on this, from the audience here, or on anything else that you find like maybe this an open question still?
I have one question.
Sure. There you go, Arnold.
Concerning the thickness of your anode material, because you are making lid structures on a graphite anode, and then the question is how thick is the anode? Because the lid structures are typically a few 100 nanometer only, and your anode is typically a few 10 micrometer.
Yes. I mean, you are talking about what is the thickness of the anodes that we process.
Yeah.
This is between, I mean, tens of microns, yes.
Because to increase energy density or things like that, you need to maybe fully structure through the anode material.
No. Oh, okay. The graphite, I mean, the anode is not only graphite, so it's not a solid graphite. It is a powder, graphite powder. I mean, also I have to make clear that we were testing not with graphite. Graphite is the most used. We were testing with lithium titanate, right? But anyway, in both cases, what you do is you have a powder of the active material, graphite or titanate or whatever you have. You mix that with a binder, which is typically a polymer, PVDF or any other polymer, CMC, and then you add a conductive additive because the polymer is insulating, and you blend this with organic solvent and you make like a paint, and then you paint on the current collector. So it's not a solid processing. So it's a liquid on the copper current collector.
Okay, that was a good point. Maybe Arnold, do you want to tell us a bit why you know so much about lips and what you are doing at Fraunhofer-ILT? Maybe that's a good opportunity now.
No, we have a lot of experience on surface structuring with femtosecond and picosecond laser, and especially scaling up the power and the speed of surface structuring is one big issue at ILT, because we now have available kilowatt femtosecond lasers, and we are right now developing multi-kilowatt up to 10 kilowatt femtosecond lasers in our lab, using high-speed polygonal mirrors and also multi-beam approaches to come to that point, which has now been addressed in the previous talk on large-scale structuring of surfaces. But there is still an issue how fast we can go and reach a meter per second web speed at a large scale. So that's still a topic.
So you're also hunting for fast scanners, I understand.
Yeah, and also it depends a little bit on the application, what has to be done. Making, let's say, three-dimensional structures on surfaces, dedicated structures, that's then more multi-beam approaches with single beam modulation. When you are looking on large-scale surface modification, that can be something with polygonal mirrors, because then you have to cover the whole area. So it's both. It depends a little bit on what you want to do. Yeah.
Very good. So I guess I saw another question from United Spectrum. Is it? Yeah, you can ask.
Few questions. First question is, I just wanted to understand what is the wavelength you have been used for this.
You mean for the current collector processing?
Exactly. What is the wavelength you have been used? Whether it's a blue or, because nowadays blue is also emerging for laser welding, especially for.
To be honest, I do not remember. I can look for this information, but I don't have it. Okay. I mean, maybe, I may need a couple of minutes to find this.
No problem, no problem.
Ainara knows.
Yeah, maybe
I know it.
Yes.
It is 1 micron, 30 nanometers.
Okay.
It is infrared.
Okay, fine, good, okay.
Yeah, that is, I guess, also for LAMPAs is a bit of a standard laser wavelength. So nothing exotic.
So you're doing basically a laser structuring both on copper current collector as well as the anode, or?
No, sorry, yes?
You're doing a laser patterning on the anode as well as the copper current collector?
Only in the current collector.
Okay, which means you are doing patterning in the copper surface.
Yes.
If I see this schematic, it shows that you're doing laser patterning on the copper material.
Yes, that is.
And then you apply the anode as a paint.
Why not in aluminum? Why not in aluminum or aluminum collector? Yeah.
We are.
Oh, it's okay, fine. Okay, I got it.
We are also doing that.
Yes, I see Tim waving. There you go.
Maybe a short question. Do you expect any change if you change the wavelength or change the ellipse structure? So from 1 micron to something like 500 microns or so, 500 nanometer, do you expect a change if you change the surface topography? So maybe there's room for improvement for the future?
We have played with different processing parameters, right? And the ones that I show are the best performing ones, right? So we change the direction, the way the pulses are done and everything, and these are the best results that we got so far. I mean, I don't know if Ainara can confirm if we have more room to explore, but I mean, you have some time the project and.
Okay.
The thing, I mean, we made some tests with the green, with the second harmonic of the infrared. But the thing in this particular application is that as you decrease the wavelength, you get the structures with smaller periods or let's say higher resolution. So as you then have to apply a kind of paint on it, the particles need to be able to fill the channels you are making in the current collector. So if we decrease the size of these channels, it is more difficult for the particles to get inside the channels.
Yeah, this makes sense.
Yeah, and in this case, if you reduce the size of the particles, then you get more expensive material for the anode, right, Miguel Angel?
Yes, I mean, we already had to move away from graphite and move to this lithium titanate because it was the, let's say, the only commercially available material that can be bought in nanoparticle shape, right? So yeah, this was the reason to use also titanate, which is, on the other hand, is one of the materials used by Toshiba to make the batteries. Okay.
Very good. So thank you very much. I guess we had a bit of discussions already about the batteries. Maybe it's better to go on now, and then we can, of course, talk about it even later, because we have another newcomer. So we have Dietmar from Ramteid, and now is his turn to show us a bit his expertise. There you go. Yes.
Hello,
you're already sharing?
you.
Yes.
Yes.
The floor is yours.
Okay, thank you. So hello from my side also. My name is Dietmar Scharf. I'm the CEO and founder of Ramteid, a company based in the southern part of Germany in Bavaria. And I want to say thank you very much for that invitation, to get that really epic chance for presenting here and getting into contact with other interesting partners in that area. So what I want to present is our computer and machine vision skills that we use in multiple other research projects to provide vision-based 2D and 3-dimensional surface scanning and metrology solutions in the mesoscale for the other project machines and prototypes for those. Sorry. Now it works, sorry. So the first project I want to present to you is a 4D hybrid. It's a EU Horizon 2020 funded project, finished end of last year. And this was about a mobile robot platform, which is also able to vertically climb on flat walls, flat surfaces, to doing inspection and other measuring and metrology applications in even harsh environments, but not only doing an inspection, but also performing additive and subtractive surface treatment functions, like in this case on this robot that you can see at the very left side of my screen. So this was developed in that project, and it uses a cold spray gun for surface treatment in this case. So the camera that you can see at the top in that yellow circle is a 2D and 3D scanner, which uses the 2D imaging from that scanner for corrosion detection and other visual seeable detection tasks, and the 3D capabilities for 3-dimensional defect detection, so deformations on the surface. Beside this, the scanner solution is also able to do the path planning for the repair operation for that robot with that cold spray gun mounted directly on the robot. So this is more or less an autonomous platform used for surface treatment, for example, on the hulls of ships or tanks. And our solution that we provided here is 2D and 3-dimensional surface defect detection. What you can see here in that screenshot of our software on the left-hand side is a live view image, and this is the middle part is the 2-dimensional processing of that image, so the corrosion detection. And on the right-hand side, you can see a real online and live view of the 3-dimensional surface, which found here a deformation in size of 0.5 millimeters that will then be planned for being repaired with that cold spray gun at the other part of the robot. So the field of view of the camera is about 10 by 10 centimeters, and in the z-axis it's about 5 centimeters. And the very important thing is that everything here works online, so the scanning is performed even during the operation, during the movement of the robot, at a precision of up to 50 microns and a resolution of up to 100 microns. And as I said before, it can detect 3D defects better than 0.5 millimeters in depth or height or any other shape that the algorithm might have to detect for being repaired. This project gained the Innovation Radar Prize 2019 for the most innovative project last year from the European Commission. So we get highly decorated on that project. Beside this, we are working another project called FemtoSurf. Later on, Wieners from Femtica will also present another part, more or less the laser structuring. And I'm presenting the vision-based scanning of the surfaces, not in the, as I said at the beginning, not in the nanoscale. This is another project partner. We are working in the mesoscale. So if the surface texturing is not only happening on very flat surfaces, we are detecting the actual surface structure so that the pattern can be perhaps modified for that non-flat surface structure that might be at that workpiece being processed. We are using for this, so the current prototype of the machine can be seen here at the very left. So this is a machine in 3 meters size, so 2 by 2 meters in the X and Y dimensions, and in size and height about 3 meters, with all the laser infrastructure mounted ahead. So we have a 5 degrees of freedom rotary and movable table, which holds the workpiece, and the laser can be directed to practically every area of that workpiece. We started with that flat workpieces that you can see here. This was provided by Femtica, and we did our scans. And here you can see at the very right side that nano pits or micro pits in this case performed with the laser surface technology from Femtica onto those metallic objects. And we are using our scanning technology with a multi-camera setup of multiple, we are not yet sure how many cameras, at 12 megapixel resolution, at a very high-speed interface for getting the possibility to use it as a single-shot point cloud generation and fusion algorithm. So this can, or the intention is to really use this in process and in real time. And therefore we need that setup, and also therefore we need a dynamic calibration of more or less pairs of cameras. So each of the camera pairs that can be formed of those 2 or 6 cameras will do an individual stereography algorithmic calculation, and all those point clouds generated from those camera pairs will be fused together to have a 3-dimensional and very high precise representation of the surface of the workpiece. And for doing color imaging, despite we are using monochrome cameras, we are using an RGB illumination for intermediate images taken for getting a color view also of the workpiece. So the general field of view of our system is 10 by 10 millimeters in size, and in the z-axis up to 2 millimeters. We are not finally defined completely, so it's 1 to 2 millimeters z-axis resolution or field of view. And we achieve from a vision point of view a precision of 3 to 4 microns, and the point resolution of the point clouds generated will be in the area of up to 10 microns in this case. Beside this project, or these 2 projects, we also were involved in a lot of other research projects from the EU on FP7 project, White-R, and all those projects. We provided our vision technology in order to scan metallic surfaces at a very precise level and provide this even in a real-time or near-time feedback loop to the processing unit of all those machines designed here. And what we are in general are is we are vision-based metrology experts for novel projects, and that's also what we are looking for. We are looking for partners for other research projects or applications for research projects which need vision experts in their partnership.
Thank you very much, Dietmar, for a great presentation. I am quite fascinated of how many European projects you have participated. I also see that you are already preparing one. This is an EPIC event. EPIC is about collaborations. There's a question that normally people get when they are no users, which is, what can you do for them and what can they do for you?
So what we can do for them is really to provide our vision-based skills and provide our solutions to tailor them in a very custom-specific way to their applications. So we are not providing a solution for large-scale distribution. We are providing solutions for a very specific use case and a very challenging, novel use case.
All right, so basically we have a good set of companies here. I want to understand a bit from the system integrators, the kind of needs they have for inspection systems. Not only Ramteid, but we also have in the audience, we have companies like NIT, we have companies like Horiba. So I want to look at Raúl now. He gave the opening presentation. Raúl, when it comes to metrology, inspection, and imaging systems, what kind of cameras do you use, or do you recommend your customers to use when they scale up your process?
Well, it's complicated to recommend to customers because they, of course, they know much better than me their processes. But in our case, we needed to find something the most flexible possible because we have a lot of different projects for a lot of different businesses. And after analyzing several methods or machines, we thought that the best solution for us was the confocal microscope because it was able for us to see something that with advanced focus variation microscope we were not able to see in our microstructures. So that's why we decided to go ahead with it, and that's the tool that we use.
We also have one other service provider, system integrator, Forjet. Tobias Dyke, thank you very much for being with us this afternoon. How are you doing today?
Oh, I'm all right. Taking care of my kids, kind of half being here, half taking care of the kids. So.
Tobias, you sound perfect, and I should know that Forjet is the iconic company that is really scaling up to large production, the surface structuring. Could you tell us quickly what Forjet can do for the rest of the people, and what can the rest of the people do for Forjet?
Yeah. Well, what we're working on is really to look into surface structuring and functionalization of surfaces, to get them to the industrial level. So really to take it out from the labs of the universities and the institutes to really apply it in on larger scales. So this is kind of what we're set out to, mainly focusing on interference patterning, but also looking on in the other technologies like the lips we had earlier. So this is something we are looking into, and that's what we're really interested in, and especially projects that are closer to industry already, like that are really kind of we're really looking at an application.
When it comes to the inspection, we just heard the presentation from Ramteid, but also we have almost every wavelength represented today. What kind of needs do you see for inspection tooling in the surface structure business?
Good question. I think there is a lot of tools available that can, from direct measuring of topographies or like just optical inspections, to all kind of scattering inspections where you look at the refraction the reflection image. So I think there is quite a I don't see a big special need that is not already there in the market.
I have you on the phone now, Tobias, so I cannot not allow myself to ask you something. In the beginning of the presentations, my very good friend Reinhard Volker raised a very important topic, the topic of IP. He said that many companies, especially in the consumer electronics market, in the mobile phone market, seem to be blocked by patents being already applied for technologies that perhaps were not mature enough to satisfy those demands. How does Forget, since they are so close to industrialization, how does Forget deal with the IP issues in surface structuring?
Well, it's not always easy. It's definitely an issue, and I think that's something we also found in some fields, that you have a technology ready and then you're blocked by some IP. But yeah, in general, it's quite a complicated topic. So I think there is no kind of best way to go or whatever. Especially, I think the IP situation. A lot of times, it's not really clear what is actually included in the patents and what is not. So that makes it even more difficult. But that's a big part that we have to deal with, taking a new technology into industry, really. But I think there's probably the whole group of people might have the same experience there. I don't know.
I'm going to bounce the question back to Reinhard, back to Neuchâtel. Reinhard, SUS Micro-Optics already has made an impact in bringing micro-optics to the automotive and the consumer world. That's not a secret, that's public information. So how have you dealt with these very IP-protected markets?
Yeah, that's always an issue. So honestly, in 20 years, SUS Micro-Optics, we never made a patent. We never invested in a patent, but it was always our partners who made the patents. So, especially what I was saying about this Rochester Photonics case, where everybody came to us and said, can you do it? And can you do it? And can you do it? And we looked in the patent and said, yeah, we can do it, but we're not allowed. So, we also recently got an agreement with Fraunhofer for the light carpet. So we are licensing now the patent. So I once learned from one of my mentors, Bill Hugel, the first president of SEMI, and he said, patents are for big companies who can defend it, or for small companies, if you want to sell the company after 2 years and you want to create some IP. If you're manufacturing, if you got a core technology and your core technology is freedom to operate, that means I'm doing this since 20 years, nobody can forbid it. Now your question is, do you invest in your excellence or do you invest in your patents? And you cannot do both. So I think maybe I'm wrong, but
you are never wrong. Basically, SUS Micro-Optics is a company that has made a difference in the field of micro-optics manufacturing. You mentioned already the light carpet of the BMW, which is a beautiful and successful story. But today we are talking about laser-based surface structuring. Do you have a challenge?
Everything has been patented. Everything has been patented already 15, 20 years ago. It is only people forget about the patents.
No, with the patents,
I'm very sure. If you look in these complicated nanostructures, surface structures, whatever, it is only you don't have the right keywords. If you look into patents, you'll find a lot of patents. Diffractive optics, random diffusers, all surface treatment. This is all many patents. You could get a patent today, but the patent is not worth because they just forget that there were 10 other patents on that.
But I wanted to talk to you about something else as well. We talk about the manufacturing of optics and micro-optics. Do you have a challenge for the companies today here doing laser-based surface structuring?
The challenge is always the same. The whole femto world, 2 photon, whatever, 2 by 2 millimeter is, we can do perfectly. We have to work hard to make it big. That's the one thing. The other thing is reproducibility. The third thing is surface roughness. So everything is a diffuser and you always lose some 5 to 10% of stray light, which doesn't make it applicable, and everybody is developing the technology, but not looking for the market or for the niche where you can really make money. And I tell you, if you look at 5 nanometer perfect structures on a 300 millimeter wafer today, and an ASML stepper is doing 280 wafers, 300 millimeter, that's a pizza with 5 nanometer structures per hour, which gives football fields per month, then there is no need for most of your technologies if it is not really better in one niche market. So that's the whole nano story. So
today we really tried our best to study all these different markets. Benjamin from Infine already had the first taste. There's a company in Dresden, Fraunhofer-AWS, who is actually working with many of these different users. I want to go to Dresden now. Tim, what can you do for the rest of the community? The floor and the attention of everyone is yours.
Thanks, Jose. So actually, we are, I have to say, not a company, but we are a research institute focusing on, let's say, technology transfer, as Fraunhofer is, let's say, known about. And I would like to say hello to everyone and also show you a little bit about the the stuff which we are doing in Dresden on the surface functionalization. So laser structuring is the topic of today, but of course it has to be a need in the end, or there needs to be a need. And what you see here is some examples. So in the middle, you see some sort of high-speed structuring for decorative applications using a scanner. Left-hand side, a little bit more in the field of wettability, and the right-hand side, you see actually what we do is industry transfer of some working solutions with integrators in the end. To tell you a little bit about Dresden, very brief, is so it's a very nice city in the eastern part of Germany, and we have a lot of rainbows, as the picture suggests, but of course we have also some clouds sometimes. But actually, I would like to make you familiar with the Center for Advanced Microphotonics, which is CAMP in short, and it's an some sort of alliance, I would say, between the Technical University and the Fraunhofer IWS in Dresden, and we make all the work from basic research to industrial applications, focusing on a specific technology which was already mentioned in the very beginning. It was direct laser interference patterning. And actually, very brief is also that we are inspired somehow by nature, of course. So I mean, most of the people which are dealing with surface texturing know the lotus effect, and they know the shark skin and other effects. And actually, if you take a closer look on the surface texture, you see that they are very special, they are unique, they are hierarchical, very complicated in most cases. And actually, the goal is and was for many, many years, even decades, to bring that on technical surfaces and to address anti-icing on airplanes and deal with friction or biofunctionality issues. So as was shown before by Marilys. And this is also, of course, in our aim. And we have let's say, different collaborations going on. So on the European scale, it's these 3 projects, so Laser for Fun, Shark, and Prometheus. So everyone has a different, let's say, scope. I will come later to that. Basically, what is usually the idea is that a particular surface texture has a specific surface functionality. And so in principle, we are developing this large area surface functionalization using direct laser interference patterning. And what you see here is actually what you can do with it. So you see a SU, let's say, of different surface texture on metals, so stainless steel, for instance, polymer like polyimide or imide. You see even glass structures and so on, and also different used by or created by different laser systems. So from the nanosecond down to the femtosecond laser pulsed laser, let's say, duration. And actually, it can be quite complex structures, like in the upper left. It's some hierarchical structure, it's some stacked surface structure, and usually you have a broad variety of different patterns. So it can range from around about 180 nanometer up to 30 micrometer. This is usually the ballpark where we are operating with this kind of technology. And there's always, like in all cases, a lot of questions in this discussion we're dealing with the process speed. And of course, the process speed is always the key, especially for industrialization. And we are targeting at very high, so 2 to 5 micrometer, sorry, 2 to 5 square meter per minute. Exactly. So, and maybe, so going from the texture, of course, there's always the goal, they need to have a use for specific things. So with application example. And what is always appealing, or what is always very illustrative, is the decoration or product protection. So for instance, on the lower right, you see Bart Simpson. So done by diffractive colors, some sort of real colors. Then you have field of derivology in the lower left. You have light guiding, what was mentioned before, cell growth, so biocompatibility. And of course, a very big field wettability, which is in the focus of many applications. And I have today for you, let's say, 2 application examples, because I think from my point of view, this is what counts in the end. Done recently. This is one done in collaboration with Airbus, and here the target, and this is a target for many, many years, to focus on anti-icing. And as you might know, such a wing is also a very big surface, so you need a technology which has a high process speed, and of course you need to show the functionality. And the goal was here to reduce ice attachment on airplane surfaces by surface texturing, and then test it in a wind tunnel to show the functionality. And of course, as you are aware of, there are a lot of different laser texturing technologies out there. So we have here lips, we have interference patterning, dilaser writing, so many different things. And actually, we were able to show actually that this kind of technology, this kind of approach is the one who outperforms the rest, so to say, because it has some hierarchical structure like in the nature compared to the others. And with that, it was possible to show actually that you have some sort of self-limited ice aggregation, which means that the ice falls off under certain conditions, like shown on the lower right-hand side. And additionally, since a lot of activities goes into the green, let's say, energy direction, you need also less heating for bringing off the ice from the surface. So once it has, let's say, developed. And the second example is focusing more on contact performance, so completely different field. So going away from, which is something which is related to wettability, going more to some sort of contact performance, contact behavior. And here there was a collaboration between the partners, development of next generation electrical connectors. And therefore, of course, you also need some sort of technology which is capable of structuring huge amounts of components in a short period of time to be productive in the end. And this is, of course, a goal and also the tendency of many efforts in the past to speed up this process. And of course, this is in every case related to the power of the laser system. And basically what you can show here is that you can, for instance, encapsulate oil into the surface and then reduce the plug force and also the electrical resistance. So very interesting for the future, for electrification of the for instance, cars, or even for autonomous driving. It is, of course, makes the connectors in the end reliable. And therefore you need a way how to do it. And I've already prepared some sort of slide to actually answer the questions which are always asked in the EPIC meeting. So what we can do for you is, as you hopefully have seen, is you can contact us in case if you need some, or if you are interested in the collaboration in laser surface engineering for large areas or high-speed applications. It can be even low speed, so it's also okay. And the field itself is very broad range. It can be wettability, has been shown, anti-contamination, biocompatibility, adhesion, whatsoever. And what you can do for us is that we are interested, I've seen that already in the talk before, that we are interested in, of course, the surface capture and the processing in the end of complex parts. So 2D is also, of course, interesting, even large scales, but 3D is very important. And last but not least, of course, the development of deep UV laser sources, which are interesting, for instance, for polymeric materials and also for small periodical structures. So this is, as most of the laser developers knew, it is an issue. So it's not so easy to develop stable sources which are stable on the long term. but they are definitely interesting for from the application point of view. So to close it, so we are definitely looking forward to exciting collaborations on the industrial scale or R&D or scientific collaboration. That's very interesting for us, definitely. And with that, I would like to finish my talk and outlining also some very important projects. So Laser for Fun was the collaboration with Airbus for the anti-icing. So Shark is on how. So we have heard that from Raúl, I think. One goal is also to predict which laser parameters you need before you actually do a shot. And this is very important. So we are working also here with a very great consortium. And Prometheus is actually dealing with a multi-kilowatt development of multi-kilowatt laser source for scaling up the technology. So 2 to 5 square meter per minute is the goal. And Lampas is definitely a parallel project which is aiming also at this very impressive processing speeds. So then I'm done for today. Thank you.
Thank you very much, Tim. Yeah, that is definitely another view of technology we have heard already about, and also a new application. So that's really important. So if I remember correctly from your last slide, it was, of course, a very good one for epic meetings. I would say you mentioned that you would like to look for collaborations for the metrology side. So that's why you were referring already to Dietmar, and also maybe on the manufacturing side of laser or system integration. So maybe I would open a bit the discussion to these two areas that were represented here. So I don't know if Dietmar wants to start commenting on the request or what you can do for Tim.
Hello, can you hear me? I think yes. Okay, great. So in general, we can provide, as I said also in my presentation, specific solutions for the specific applications. So as high speed is always a problem, for example, for laser texturing, it's also very important to do the control and measurement process also more or less in real time. And that's also for our project that I presented for FemtoServe, the main and most important goal to really do also the measurement more or less in real time, high speed, single shot processes, as we have for reaching the precision and the resolution that we intend to reach, only a very short and small field of view. And therefore we don't have much area to cover at this precision, and therefore time is the most important and most critical thing, and the imaging algorithms are very challenging in this case. And to really provide this in real time, you need massive performance and processing capabilities in general.
That's quite interesting. So is there, so you mentioned that in your presentation that you have a somehow lower limit of the resolution which you can, let's say, attain?
Yeah, with visual-based applications, I can, or the maximum attainable resolution is 1 micron. So okay. This is the wavelength, of course, in this case. But we are nearer to the physical limits with vision-based solutions.
Yeah, okay. But this is quite interesting for many applications. So the lower limit, so 1 micron is for many applications, it's quite okay. So it's good. Mm. Okay, so maybe we can exchange somehow later about.
Yeah, of course, great. Yeah, for sure.
Thanks.
I wanted to hear the magic word. So let's exchange our contact later. That's why we are here. Very good. So I see Benjamin has a word to say. There you go.
Yes. Hello. Yeah, thanks again for the great presentation. And maybe if it fits, because Infineon has also a big facility close to your spot. And I heard you're doing a lot of interesting stuff, maybe not just on surface texturing. You have one platform that I would really like to see in person. But anyhow, I was wondering, since we often talk about the wings of, let's say, the Airbus to make it functional, is not the first step maybe to do all these sensors that checks the pressure and all these stuff to make them functionality with being free of icing and all that stuff? Would that be the first stuff? Not the big wing. For me, it looks very complicated to do a big wing.
Yeah, that's true. So the goal, of course, is relatively high to say, okay, we have a long-term goal to address it or to achieve it. But you're completely right. So if you remember, for instance, there was a flight many years ago from Brazil to France, I think, a machine where the sensors froze froze during the operation, and then the machine crashed. So definitely there are more than just the wings to be functionalized and to have some, for instance, anti-icing application. I mean, you can also go across this border of aviation and go to turbines or whatsoever. I mean, there are a lot of different applications where you, because basically what is the main thinking behind that is it is some sort of anti-sticking surface. So it can be anti-sticking of ice, it can be anti-sticking of some particles, and so on. So we heard that before. So for instance, if a structure is smaller than a certain particle size, then of course it doesn't stick so good to the surface. So we look into many of these kind of applications, and it can be quite broad-ranged. But you're right, definitely. So you can start from small parts and then go up.
But from your knowledge, there is no sensors already flying around which are functionalized some way. No?
At least I cannot. Let's say in principle, this is some sort of milestone. So because this goal of showing an anti-icing surface operating under real conditions and showing this effect, this is really a milestone which was not shown before. Yeah, and this is actually the great thing about that. And then, so maybe I don't know if you have something in mind which goes in this direction. So maybe I don't know if we should talk about that, but I think it opens up, let's say, the doors to many applications.
Yeah. All right, we have a lot of femtosecond laser companies in EPIC, and if you follow these meetings, you know how crazy Francesca and I get when we talk about femtosecond lasers. All the way from Vilnius, Lithuania, we have Ivaras from light conversion. He said you mentioned development of a deep UV laser source. Can you give us a bit more to chew up with this? Well, he said, what parameters are you looking for?
So first of all, so deep UV would be something like below 300 nanometers. So usually in interference patterning, for instance, the spatial period which you can achieve is related to the wavelength. So this means the lower the wavelength, the smaller the feature size which you can produce. And the let's say, so stability would be definitely interesting. So okay, I mean you have the pulse, the pulse energy is it depends a little bit on the let's say the areas which you would like to treat. But of course, first of all, it needs to be an industrial ready system which can be used for the processing. So I'm not sure femtosecond is even a little bit really femtosecond deep UV is, I would say, really challenging, isn't it?
It is, and I think we have a lot to discuss on that, and I have somebody from class 5 smiling about this. You have something to add on that?
Yeah. I thank you, Tim, for this nice overview, which was really interesting. So what we do at class 5 is basically building like the next generation of, or we started the company building the next generation of scientific lasers. But I was always curious during the last years about potential industrial applications. So the commonly used lasers are basically hundreds of femtoseconds long in pulse duration and have fixed wavelengths of about a micron. What we do at class 5 is basically we upgrade this type of lasers to get to pulse durations below 100 femtoseconds, even down to 10 femtoseconds, to enable completely new regimes of intensity or material interactions. And on the other hand, we basically extend the wavelength ranges to go to the infrared to 1.5 micron, 3 micron, but also in the other direction towards the deep UV, for example, something like 205 nanometers or even shorter wavelengths. And we believe this could potentially enable a much larger range of materials that could be processed. And I would like to know your take on this, like not only talking about the deep UV, which is very interesting for us because we do femtoseconds in that range, but also about the infrared.
Okay.
Robert,
definitely interesting. Yeah.
Thanks a lot, Robert. Team, your presentation was spectacular. You mapped all the different applications from femto, pico, and nanosecond. We love you for this. That was really great material. Actually, your anti-icing structure raising a lot of interest in YouTube, in my email. Harald Walter from Kinegram is also wondering a lot about this. I will forward you the question. That was fantastic. And we're going to move to the next speaker. Next
I have one more question. Sorry to interrupt. Kim, Dr. Kim, thank you for the presentation. I have a couple of questions in your presentation. First question is, you told about the removal of ice, especially in the aerospace application. May I know how long the laser structuring can retain its structure, or how often we have to do this structuring?
Yeah, okay. So good question. So actually, this is exactly the next step. So once you showed how it can be done, so now you need to prolong the lifetime actually. And we at the moment have, for instance, in this particular case for the anti-icing, we have some application tests running on an A350 flying around Europe and actually testing things like, or let's say, allowing for testing and investigating the stability of the structure, the effect stability, and so on. But from the application point of view, this is, let's say, the next step to make it more reliable, more stable, and so on, because we're dealing with an area which hopefully after the crisis will recover. But of course, it's dealing with passenger transport, and then you need to have a very special care about functionality, stability, and so on.
Okay, so you are targeting on turbine blades or entire wing?
We at the moment are completely open to that. So the particular functionality was aiming at the wing, the front wing, so the leading edge. And this was actually shown in the video. So in principle, a structuring of a complex, it's called a NACA profile. It's a very complex, I mean, not so complex. I mean, it's an aerodynamic surface, but of course it's a 3D surface. And in the first stage, we structured the first part, the first area on both sides. But of course, I mean, usually, and this I think is maybe also related to the question which arose before. The question is, where do we need it most urgently to allow for a stable operation? So this is step by step now done in order to see where are the, let's say, the most interesting points to go
Team, the polygon scanners of Lars really had the solution to go into large surfaces. Lars, thank you well for being in Koningsdag with us.
One last question.
We'll move to the next one. So Lars, thank you very much for being with us. The floor and the attention of everyone is yours.
Okay, thank you, Jose, and also congratulations with the king. My name is Lars Penning. I'm one of the founders of NextGen Technology. And I would like to show you some slides on what could be possible when using polygon scanners for laser processing. Short introduction. 2011, we released the first polygon scanner system, and our background is graphic arts. So we use the know-how from the graphic arts to transfer into the laser material processing. So because at that time the first ultra fast pulse lasers were introduced, picosecond lasers. So we're using the technology from graphic arts, and we tailored that for handling higher powers and larger red plates. It's a polygon scanning, but it needs much more than just a polygon, a rotating polygon. You need the f-theta optics to focus the spot. And that is where we introduced mirror optics instead of glass optics or refractive optics. So full reflective optics. So we have some advantages with respect to thermal loads on the optics. In addition, we introduced a proprietary singularization method in order to achieve or to keep the high positioning accuracy and high repeatability, even when increasing speeds. We're located in Belgium, and since a few years we are associated by ScanLab, so we use both of best worlds, ScanLab is known from the Galvo scanners. And we try to merge technology in order to service our customers with the best solution. Here on the throughput, on the right side you see some data on a polygon scanning. Now a typical scan speed it can be ranged from 25 to 100 meters per second, but we go much faster, which you will see in a second. To give an idea on the throughput lines, 400 lines per second, full telecentric. So in this case, a 6-inch wafer, but we also have a 12-inch wafer size, which we can do full telecentric. And of importance, of course, the high repeatability in micro machining. So that is where the synchronization comes in. High throughput laser structuring. LAMPAS has already been mentioned. It's about applying nanotextures, just introduced by Tim, inspired by nature. And the idea is, of course, how can you apply those surface textures in a cost-efficient way? It's all possible on a square centimeter. Everything is possible. But the industry is about square meters and not about square centimeters. So one of the objectives in LAMPAS is how to reduce the square meter processing cost of such a laser-based process. On the right side, you see some companies involved in that process. Those are well-known companies. I think for the people who do not know, BSA is Bosch Siemens Hauser Geräte from which has a facility or several facilities, manufacturing plants in Europe. That is also where you want to have clean surfaces in household appliances. It's always nice to keep your kitchen clean, and especially nowadays in the situation with the corona. Yeah, I don't have to explain that. Some basics. We've seen that image quite often already. So if you look at a laser application, you can break it down in different components and processes. First, you need the process. Now, in case of a DLIP process, which just has been explained by Tim, that is the process. It's a multi-beam focused in one spot, and that makes it already somewhat complexer than the traditional single beam scanning. You need a laser source, you need a scanner system, and you need motion control in order to apply the features in an accurate and precision way. So what do you need to do to reduce the square meter processing cost? Of course, number one is increasing speed, but increasing speed also requires more laser power and also more pulse frequency. So what we need to do is deploying a laser or develop a laser source which is able to deliver high power and high pulse repetition rate. Now, to give some idea on what the effect is of increasing pulse repetition rate on scan speed, is that you will see the scan speed increases if you move up the pulse repetition rate. And in case of the LAMPAS project, we have a 10 megahertz laser source, which gives you a ballpark figure of 250 meters per second. It of course depends on the process parameters, but let's take this as an example because that's close to the reality. So what you get is quite a high scanning speed, with 250 meters per second. That's 10 times faster than a really fast Galvo scanner. So that gives you already some idea on what is happening on the throughput. If you look at the square meters throughput, if you look at a polygon scanner with those kind of scan speeds, excuse me for that, then you're going to up to quite some square meters. Note that this is quite small features. It's not really applicable to the DLIP process because that's much more. That's more in square meters per minute. If you look at the, what does it mean if you increase those scan speeds? And what does that mean for your square meter processing cost? Because that's all about what the customer is interested in. What does a square meter cost to process it? Now you see that even with those higher scan speeds, you can really get a good, interesting cost benefit, which open up all kinds of possibilities for trading in established techniques by a laser-based process. To give an idea on how to increase throughput much more, so we talked about scan width. We have 6-inch, we have 12-inch, but what if you want to do square meters, like air wings or displays or that kind of solutions? Now then you can go into the multiplexing or the stitching of solutions. Now, this is also a technology well known in the graphic arts, and we also move that from graphic arts into the laser material processing. So here you see a 900 millimeter or somewhat more than 900 millimeter scan line length multiplexed, and that is the way how you can process square meters with the latest advance of ultra fast pulse lasers. So that's my short introduction on the polygon scanning, and I think I've touched a few topics which have been addressed in the earlier presentations. So
Thank you very much.
Yeah. So if there are any questions, I will be happy to answer them. Or
sure. So Lars, thanks a lot for your contribution. Yes, yeah, Dietmar, go.
Most of the talks were on structuring flat surfaces. So for non-flat surfaces, curved or more complicated surfaces, so for real parts, and structuring not only one side of a part, but a really whole part, even at the edges, are there appropriate solutions for adjusting the pattern in real time to the real topography of the workpiece?
Yeah, so right, that there's always a compromise you have to do with improving scan speeds. So the dynamics is much different from a traditional galvo scanning approach. So you have less time to do active corrections or whatsoever. So this is really a technology which is for flat surfaces. And yeah, there are ways to convert flat surfaces into a curved surface. But if you want to go into the really curved surfaces, like the dental implants or things like this, I think it's more a fit to the galvo scanners, what also Mr. Gilner just touched an hour ago. So there are different approaches. It depends on the application, what the best scanning approach is.
Very good. Then do we have other questions for our leader, our hero in Lampas for for scanning opportunities? And there we have Ben. Yeah, Ben, there you go.
Yeah, talking about flat surfaces and cutting along the line, semiconductor industry says hello. So I was wondering, I mean, we always see the nice pictures where you compare nanosecond and femtosecond, and nanosecond looks super bad, femtosecond looks perfectly nice. And in theory, it is like that. But if you don't have a polygon scanner, and as you just mentioned, and if you cannot move fast enough, then you will lose that effect of cold ablation, and then also your femto will not bring you anything. But my question is, when do you think the polygon scanner will be really part of the industry? And are they very stable, or are they service intensive? So what's the status of the polygon scanner? Because now you see a lot of linear movements and you see a lot of galvos running in the industry, but not so many polygons. And I was wondering, I mean, I think it's a great idea to do with the polygon.
Okay, so now to be honest, most of our systems are being sold in Asia. So not that in Europe, it's more in the R&D, still in the R&D environment. Polygon scanners are out there for 30, 40 years already. So it's a really solid technology because it's continuous rotating motor. So you don't have the issues with drift like you have with a start-stop movement with galvos. So from a reliability point of view, polygon is very, very industrial rod. So there's no. The topic, however, is that it's a hardware implementation of a raster scan. So there are not that many applications. It's not flexible. So you really have to tailor the solution for the scanner system. So that's why we chose for two sizes initially, for the 6-inch size and for the 12-inch size, to cover that area in one single scan line. And that is where the applications are for NextScan. And I will be happy to serve you with a polygon scanner solution which can address those sizes for you. And I can give you the feedback on reliability and repeatability. That's available.
Do you have an application lab?
Yeah, we have several application labs, but we are in Belgium. We have a demo lab. We are not process developers,
okay,
but we can demo the functionality of the systems, and yeah, that's for sure. Yeah.
I have one more question. Yeah.
Sorry, I guess we have now a bit to speed up because the list of the agenda is really long. So Danijela is waiting since the beginning. She was trying to speak earlier. But Danijela, thank you so much for being here from Marilys. If you want to share your screen, the floor is yours.
Thank you, Francesca. I hope so you hear me. Let's try sharing my screen. Doesn't let me.
Okay, you should go down, not yet. You should go down where the green button, I guess, maybe you try again, is maybe just the...
Okay.
Yes, it's coming. Yes, so it's not in presentation mode. Perfect, there you go.
Thank you very much for giving me opportunity to speak today. I'm going to speak about work which we are doing in Laser Center, Marilys. And I hope so that the work which we are doing can help speeding up bringing surface structuring application to the industry. For you who are not familiar with Marilys Center, I would give just small introduction. Marilys is a part of Institute of Physics or Czech Academy of the Science. We are R&D center, which is providing diode pump solid-state lasers with breakthrough parameters. I will come back a little bit more on that. We are and we will be project of international interest. At the moment, we are running a teaming project, which is funded by Horizon 2020. If we are speaking about the location of Marilys Center, we always like to say that we are in the middle of the Europe, or more precise, we are in a small village called Donji Brežany, which is nearby Prague. Marilys has a very nice facility, which was developed in period between 2012 and 2014. Our facility has 700 square meters of laboratories and experimental halls. I promised to speak about world-leading performances. If we are printing on one side pulse energy, on another side repetition rate of diode pump solid-state systems, you will see two green squares, which are representing the Marilys laser systems. But today, I'm going to speak a little bit more of something what we call parallel laser systems. This is the diode pump solid-state lasers, which are working on thin disk technology. As you can see, parallel A, B, and C are working on 1 micrometer. That means we were using terbium YAG materials. Recently, we started exploring another materials like in parallel D. You see that we are start using volume-based materials. That means we are moving to 2 microns as well. Marilys also has a lot of know-how in wavelength conversions. That means that we are at the moment able to provide our customers and users photons between 200 nanometers up to 3.2 microns. Based on know-how, we start recently developing something like more compact and industrial grade laser. We call parallel 100. This laser has 100 watt average power, 100 kilohertz, 1 millijoule operating on 1 micron. and the pulse duration below 2 picosecond. What I would like to bring to your attention is quality of the beam, which you can see on the right side. M square of our beam, it's close to 1.1. Beside the standard laser, we start also thinking about customized solution. Here is just some of the ideas. We are open for any another. And I would like to say that this year we are delivering 2 systems with which will be integrated in processing stations. Okay, Perla C100, it's delivering 1 millijoule pulse duration, energy per pulse. That means we have to look for another approach how to use this laser. And in the first approach, we use diffractive optic element. I would not go in more details. You just see a little bit here, but let's say that with our laser, in cooperation with one of our partners, we were able to get in the same time 784 small beams. Another way to use this DOE approach is in the case you really know which kind of structures you would like to have. That means you can pre-design diffractive optic elements and then print those structures. We already demonstrated that we can cover millimeter area with just few pulses and with very high resolution. I should mention that M square for this application play a very important role. Another approach is already mentioned so many times today, and I don't have to say anything more. Thank you to Tim and his team. We were introduced to this wonderful technique. And here I only want to mention that we start experiments with 2 and 4 beams. What I'm showing here is our unpublished results on DLIP with 4 beams on steel. And what I would like to say, really with using very basic scientific setup, I would say we were able to reach 100 square centimeter per minute using only 1 kilohertz repetition rate. What we saw like main problem was that we are missing fast and precise movement of the stages. And what I would like to bring to your attention that energy per pulse, which we are using here, we can also run with a laser which has 50 kilohertz. And at the end, to answer to the magic question, what we are offering and what we need, we are offering expertise in developing customized high-intensity, ultra-short laser systems. We need the partners which will help us to really explore capability of this system for surface structure application in this particular case. That means we are missing partners which are working on scanner and optics for efficient usage of millijoule energy per pulse, and also faster and precise stages. And since main philosophy of HILAS is to produce the lasers for industry, we are missing end users with application which are really going to benefit from usage of the millijoule ultra short laser pulses. And with that, I'm finishing my presentation and I'm open for a question.
Thank you very much, Anila, for a great presentation. Thank you for keeping it on time and for telling us exactly how to help. I have a lot of companies here that manufacture optics. We are all wondering about this fantastic DOE system that you have there. Could you specify a bit more about the laser optics that you use and perhaps share some challenges with the companies today?
I think main challenge generally with millijoule lasers is laser-induced damage threshold. That's the one of the main challenge which we are having. That means it's not only designing those elements, but also design them on the way to be suitable for this energy profiles, I would say.
Do we have any questions for Danijela from HILAS? One of her key questions was about users. She said, I want to meet users. Why don't we meet? Well, we have a question from NextScan Technology. Lars, thank you well for your frage.
Yes, right. Just a short question on the efficiency of the DOE.
Yes.
Because you're handling high powers, so what kind of efficiency does the DOE has? What range I have to think?
We are just, this is what I'm saying, we're just using the DOE to structure, but what is really need now is to develop integration solution, which are going to fastly imprint those structures inside or on the material. That means, I know that Pulsar has a quite nice scanner for that application, but I think they are working only up to lasers with few millijoules in the best. And if you see our presentation, we can go up to 10 millijoules, for example.
No, I'm just asking that because in Lampas we have 1.5 kilowatt laser, and if we apply the grating, then we lose about 20% on the power level. That's
we didn't lost too much in DOE, which we had. I think the one, I can't speak too much because it's under NDA, but I can tell you that if I remember well, we lost only like 20% at the max in DOE.
20?
Yes.
Yeah, okay, so, but 300 watts, you have to absorb it somewhere, so you have to cool it. Okay, thank you.
I cannot wait any longer. Today I heard that Fagor was presenting at this meeting. I got super excited. José Luis, muchas gracias por estar con nosotros esta tarde. Thank you very much for being with us this afternoon. The floor and the attention of everyone is yours. Tell us who we can help Fagor. I think we still have you muted. You need to unmute yourself so we can hear your voice.
Sorry. Hello. Hello, thank you very much. I'm going to share my presentation. Okay, thank you very much for the opportunity of sharing with you our applications. So my name is José Luis de la Peña. I belong to Fagor Automation. I work as an optical technician in the research and development department. Okay, and Fagor Automation is focused I have prepared the 3 slides. And sorry for the presentation because I have no time for doing this, okay? But well, Fagor Automation is focused in the automation system, okay, related with machines. So we have 3 different lines. One is concerned to the CNC, okay, that control it, the numerical control, the axis motors, okay, the spindles motors. And other part is the feedback systems. Okay? All the machines has different axes where they have to move, and that the control have to the numerical control have to control. And also we have a part of service, okay, and a part of motors, okay. But now I'm going to talk about this, okay. We develop feedback systems, optical feedback systems, incremental and absolute, linear and rotary. The encoders can be enclosed or open enclosed. Or open enclosures. Okay, so what is an optical feedback system? Every feedback system, every optical encoder contains 2 parts. One reading head that is moving and one scale that is fixed. Normally the scale is fixed to the machine, and the reading head moves, and we try to control the movement between the reading head and the scale. And this movement is given to the CNC in order to control the movement of the toolings, okay? So normally all the scales are a diffraction rating, okay? Usually 20 micron pitch. This is an absolute. Here we have two tracks, the incremental track and the absolute track, okay, depending on the different technologies we have. And the working principle is the following, okay. We have a scale, okay, and the scanning head that contains an LED to illuminate the scale, and a grating and analyzer to interact with the scale, okay. And from this interaction, in some part of the space, we have a pattern, okay, an optical pattern. And this pattern moves accordingly to the movement between these 2 gratings. And in order to catch this movement, we have to put a photodiode on the space on the plane where the optical image is located. Okay, and then we can transform the optical modulation in electrical signals that are sent to the controller. Okay, so the principle is quite easy. So we are involved in the Laser for Source project, okay? And I'm going to show you here one application concerning the texturing of the scales. Okay, the scales, we have scales on glass or scales on steel tape. Okay, and in the Laser for Source, we are working with TEID. We are collaborating with TEID in order to how to texturify these lines. Okay, with a laser. Okay? Currently, we have a photolithographic project, a photolithographic process. Okay, that means that we have a master that we have to make a copy. Okay? And if, for instance, if we want to for glass, we have scales up to 3 meters. But for steel, we are able to manufacture scales up to 60 meters. Okay. But we have a master of 1 meter. So every 1 meter, we have a step and repeat process. Okay. And one of the most important things for our end users is the gap between the scale and the reading head. Okay. Because in some products, for instance, in this product, okay, we show the reading head and the scale. Okay, separately. It's like an IKEA product, okay? And the end user is the responsible of the mounting, okay? So the end user has to fix the scale to the machine, then they have to fix the reading head to the bracket in the moving part, and we provide them some tools in order to get a good alignment and a good installation, okay? But the distance between the reading head and the scale is quite critical. Okay, so for instance, one result what we have obtained in the Laser for Source project is the blue line. Okay, is the current product. Okay, where the working distance is about 0.5 millimeters, and if we have a feedback system concerning the signal. Okay, everything up to 0.5 volts, okay, it's okay. So here we have a tolerances of about 0.2 millimeters, okay. So the customer has to install the encoder at a nominal distance of 0.5 millimeters with a tolerances of 0.2. But we have observed with the texturation of the laser, okay, we are able to get ratings that they are not the behavior is not from amplitude but also from polarization. Okay, so in this case, this is the behavior, okay, of the intensity with the working distance. So in this case, we have this like a W behavior, and if we manufacture an encoder with a nominal distance from here, for example, of this, okay, the nominal and it is automatic with automatic gain control, okay. In this case, the tolerances are increased up to 0.4 millimeters, and it adds more easier to install for the end user, okay. And also, as I have mentioned before, at present we have a photolithographic process. So that means that we use resins, we use clean rooms. The process is quite slow. So our goal is to get with the Laser for Source technology, trying to have a role to a continuous laser engraving process. I mean, we have steel tape from one side, and thanks to the laser process, we have the scale. Okay, and it's faster, it's cleaner, it's more eco. Okay, and due to the presence of leaves that we have found in these texturizations processes, okay, we can the opportunity of dealing with the scales either of phase, amplitude, or polarization behavior. And also the quality and definition of lines is also depending on the texturization. So this is what we are working on within the laser for source process in collaboration with AID. And that's all from my side. Thank you very much.
Thank you very much for your contribution. So one other user added to our list today. So it's really impressive what we can hear. So are there some questions from people in the audience? Jose? Because if not the case, I would also say a bit of your challenges. I was listening. So on glass, you still cannot do laser surface structuring, right? Because you're doing mostly photolithography processes. Do you think there is a view, or is someone in the room saying we can do it on glass, or is it not possible? Let's forget it. What is the feeling in the room?
Well, we can do it in glass, but for very small dimensions. For instance, for great phase gradings, for reticles, okay, for the analyzer, for put in the assembly in the scanning head, not for the scale, but for the scanning head could be possible as phase reticles.
So if I don't see other questions, can it be? Because we have here a user, you can think about it and maybe shoot. There's Dietmar. Yeah, here you go. You are still muted.
Now you should be able to hear me. So regarding the production of your scales, what about the thermal expansion? If you have a distance of some 10 meters or so of your scale, and you need to have stable thermal conditions, otherwise your scale expands at least some millimeters at that range.
Yeah.
Is it affecting your measurement somehow, or is it enough to just know the temperature in this case?
Well, yes, when we manufacture the master, the temperature is controlled, okay, with the tolerance of 0.1 degree. Okay, we engrave at 20 degrees with it, and we control the temperature at 0.1 degree. And also when we make the copy, okay, with the photolithographic copy, okay, the temperature is always controlled, in this case under 0.5 degrees. And then all we send all the product we send with a compensation curve for the temperature.
Okay, thank you.
Thank you.
So I guess our community in Vilnius, our speakers are waiting for their turn. So maybe we can give the floor to Antanas from Workshop of Photonics. Antanas, you can unmute yourself. Or I do it. Yeah, the slides are coming. Very good. If you go in presentation mode, it's even better.
I hope so.
Well, is it not? It's not yet, but you can go like this otherwise.
So, is it unmuted? Can you hear me?
Yeah, you can. We can hear you. You can go.
Okay. So too many screens open. Okay. Can you see my presentation?
We can see the, now yes. There you go.
Okay, good.
Perfect.
So, hello everybody from Lithuania. My name is Antanas Urbas. I'm from Workshop of Photonics, and we work mostly on cutting, drilling, dicing, all the possible materials, because we use femtosecond lasers, and as one said today, nothing can withstand femtosecond pulse. So, by working on it, we thought that maybe there will be something suitable for structuring, especially if talking about hydrophobic or hydrophilic surfaces. So historically, we saw many methods today, and if we look to literature, we can see plenty of methods of doing this. One is just covering with some chemical or electrochemical surface, which can work as a hydrophobic one. Deposit from plasma some materials. And more importantly, these depositions can be put on previously laser machined surfaces. So we saw many methods of machining. I think if we speak of square meters per minute, the best way of doing it is interferometric, like we saw it from Fraunhofer presentation. But we are not strong in it, so we thought about different things. So there was mentioned that laser-induced periodic surface systems are appearing after putting some kind of laser pulse on surface. And we saw that femtosecond lasers generate tricky things like surface plasmons, plasmon polaritons. And we thought, what can we do to make it more efficient or more tricky, or maybe to use one beam instead of many beams, like it is done in previous Danijela's presentation, just by splitting in 700 beams. Can we do this or can we not? Then we were thinking how to make the pattern that may be quite efficient and covering big area of your target material. So we work with non-diffracting beams a lot, and starting from Bessel beams, we can build a lot of interesting patterns. So Bessel beam, it was mentioning in the paper that it generates quite efficiently surface polaritons, but the problem is that the area of it is very small. It's can be microns, can be submicrons, so it's not suitable for structuring, for texturing. So, but we can do the following way. You can put parallel Bessel beams, and if you put them quite close, like in left-hand picture, you can see that a lot of side maxima appear, so which can be used for texturing as well. Maybe, I don't know. I never tested, but that's an idea. So you can make a superposition of various Bessel beams of higher topological charges, like in this picture. And if you make the superposition of -1 and 3, you can see this picture, or -3 plus 3. You can see quite regular thing. This can be also sent to your target. You can use other symmetries like parabolic beams, Weber beam. Here are presented two cases of the various divergence factors. You can use elliptic beams, of various ellipticity factors. So you can put them in parallel, like it was in case of Bessel beams. You can see a plenty of maxima which can work on your surface. And if you are crazy enough, you can even combine Bessel beams with Weber beams, and you will be probably happy like this guy on the picture. So how we do this? It is known that if you focus your laser pulse into fused silica, there appears self-organized structures which are perpendicular to polarization of the light you focus. And these structures are of size of couple of millimeters, and each structure acts as the tiny half-wave plate. And if you organize these half-wave plates according to prescribed rule, you can make optical elements which change your geometric face of in your beam across the cross section, and you can control it very, very nicely. Of course, you have to control very precisely fast access position, which we do by during manufacturing, and after that on control device. And these masks can be quite simple, like this one, which is used for superposition of two high order bezel beams combined with hexagon, or happy face you saw on previous slide needs a little bit more complicated thing, especially when you have to encode amplitude and phase for far field. So what my message is about. So I don't think it will be achieving square meters per minute, but it can be used for making molds a little bit slower, but you can imprint very complicated surfaces, which can be used further. It can be used for slower processes, like it was an example of structuring of implants. Why not? And one important thing I forgot to mention, that unlike Asphericons freeform optics, this is suited for one wavelength. But if you use laser, it's normally it's not the big problem. So then answering and rising and answering the question Jose likes very much, what we can do and what we want from the community is that we can do a lot. And if we can get understanding from the community which patterns of electric field you want to send to your target, we most probably may help you with constructing, designing, and manufacturing the mask, which will build the pattern you want to get. So then, thank you.
Thank you very much for a great presentation, and thank you very much for the Workshop of Photonics always to be so active with EPIC. I went to visit you there in Vilnius, and I was amazed by all the work that you are doing. Are there any questions for Antana? Ultra fast photonics, I want you to meet my friends from Aachen, Zone X. Ben, how are you doing today? Let me unmute you. Yes, I can hear you. Te oigo bien.
I am very good, thank you. How are you?
What is Zone X, and how can Zone X help the community on the laser and also on the optics as well, perhaps Workshop of Photonics as well?
I think there's two possibilities. We do ultra precision manufacturing with mechanical processes. Probably one of the few here not using a laser. We are producing optical mirrors for laser systems. So any reflective component made of metal can be done by us. Furthermore, we also produce microstructured surfaces, but these will be structures created by single crystal machining and not by laser machining.
We are quite amazed of the work that you have done in metal optics. So whoever is looking for any kind of mirror with high reflectivity and a perfect shape, I was really fascinated by your technology on that. For the high power laser business, you guys are unique. I want to go to Austria. I want to go to Graz. I want to go to my very good friend, Paul Harman from Gianeum. Paul, how are you doing today?
Yeah, I'm fine, thanks.
I'm so happy every time I see you smiling. What do you think of the meeting so far, and what kind of cooperations do you think you can make after this?
Well, I think this meeting was very useful for some extent, but I have to go back with many of the information and discuss this with my experts, because I am not an expert in every particular field that has been brought up today, I have to confess. So very interesting for us is the metrology. I was also quite impressed of the findings of the Laser for Surf project, which I will have a look into much more detail. So when it comes, for example, to direct laser structuring of roll processes, this is a topic that has been in our thoughts already for quite a long time. And we did not find yet the time to implement this in our instruments. But maybe this is a good occasion for us to look into that into more detail right now.
Paul, you have been one of the drivers of the technologies in photonics that to go into the high volume manufacturing. You're playing now currently a huge role in the roll-to-roll manufacturing. So really happy to have you today with us. And we're going to go to the next speaker today, which is Gedvinas from Femtica, Vilnius, 3D printing and other technologies into photon polymerization. Thank you very much for being with us. The floor and the attention of everyone goes to Lithuania.
Hello, everyone. I'm not sure. Can you see my screen?
Yes, crystal clear.
Okay, perfect. So my name is Gedvinas. Today I will present a company called Femtica and also our project Femtosurf, which is about surface structuring. And at first about Femtica. Company was founded in 2013. We are based in Lithuania, currently have 33 employees, 3 of them PhDs and 5 PhD students. Femtica provides R&D services, limited production services. Let's say if customer wants to test how a idea works in real life. And our main product is laser nanofactory workstations, which was first introduced in 2017. And we already have sold at least 5 and installed at least 5 of them. And mainly Femtica works with 3 material processing technologies. It's selective glass etching, which is subtractive manufacturing, multi-photon polymerization as additive manufacturing, and also surface structuring for different materials by using ultra-short laser pulses. Also, Femtica is coordinator of Femtosurf project, which was started more than 1 year ago. And the aim of this project is, together with 10 partners from 6 different European countries, to create a machine dedicated for surface structuring. And this machine will consist of kilowatt level femtosecond laser, measurement devices, which Ramteid was talking about, and a precise robotic system, and also optical chain for beam manipulation and fast structuring. So this machine will be optimized for fast, efficient, and precise surface structuring for 3D parts, as I want to highlight that it is not for flat surfaces, but for real parts, as bone implants and boat propellers, for example. And to induce surface properties such as hydrophobicity, anti-fouling, or oscillation manipulation. And of course, answering to epic question, what can we do for you and what can you do for us? So many publications about how beam shaping can make a huge impact for surface structuring, but is very limited supply for beam shaping elements in the market, which could be tunable and also, most importantly, could handle very high power of femtosecond laser. For example, most of spatial light modulators can handle only up to 100, 150 watts average power of femtoseconds. And in this project, we're talking about kilowatts of femtoseconds. So we see huge necessity of beam shaping elements like that. So thank you. And now I'm open for your questions.
Thank you very much, Gedvinas. So yeah, we heard a bit already about these challenges about optical elements. So we heard from Masfericon already that Sabrina already suggested something. So maybe Sabrina, you can speak also with Gedvinas in case they're interested. And Also, we have Gwen later, so for K-Labs, she's also supplying lenses and optics for this. So maybe we don't give the word to Gwen now because she has already a talk later, so maybe we speed up a bit. And also, we were missing our friend from CSEM, so Mark. We are just looking, you're attending now, you didn't ask any questions so far, but we really would like to know why did you attend this meeting and what can you do for this audience? What is interesting for you so far?
Yes, I mean, for those, I think everybody knows CSEM. I mean, it's quite well known. It's a R&D company. I know we'll not present it. And yes, we also do since ages, I mean, everything related to micro and nano surface structuring. And this goes also from some topics I already heard here. It's hydrophobic, hydrophilic surfaces. We have people, they're doing that very well in Neuchâtel. On my side, we are doing more optical effects. I mean, micro nanostructures with optical effects. And a few years ago, we also developed a way how to do the nano structuring of steel, especially for holographic effects, diffractive effects, security effects, directly engraved in steel tools to, in fact, to put that on injection molding machines, such that you directly have these effects when you mold the parts. And in fact, it was quite interesting for me here to hear about laser engraving, because we, how do you say, I'm not really the specialist here, but we have some people also working on that topic, more for cutting, for also rougher structures. But I mean, if you're interested about really nanostructuring, we have a different effect of steels, of metals. We have a different way, in fact, to engrave it, not by using laser, but by using a direct transfer. And this, we actually use it for more for brand protection, security application, but can also be used for other things. Typically, one of the talk I hear, it was dental implant. I think it's the first or second one. We also developed this with our tool to do the stamping. I don't know if this could be used also for you doing the laser engraving directly on the implants. We developed the technology by using a stamping effect, with stamps of hard steel engraved with these structures.
Very good. So I guess now it's time for PLX. So we can go on with our agenda. So Michelle, if you want to share your screen and start with your presentation, the floor is yours.
Sure.
Is coming. It's not presentation mode yet, but yeah, there you go. There you go. You can start.
Thank you. Hey, so I'm Michelle Hires. I'm the Director of Engineering at PLX. So I'm just going to talk a little bit first about what we do. So the manipulation of light. So I think there's a lot of talks so far today presenting basically how to get the laser beam for surface structuring. So this is a really good application of what we do. So anything regarding beam delivery and at really high precision levels, so we're talking about sub-arc second, we do a lot of applications for us in targeting, bore sighting, beam folding, steering, any of these laser systems, interferometry, so some of those beams you guys were using for interference to put down those patterns. And we have all different versions. So we're really the pioneers of what we call this retroreflector, these invariant optical systems, to basically have the path here on the bottom left-hand side, coming back with these small deviations. And we have all these other systems that we've developed, lateral transfer, hollow retroreflectors, periscopes. But really with the heart of what we do on the bottom right is all these different types of custom OEM applications. So whatever system you guys have, we would provide the solutions that would work for you. So in our business model, we really work at the level of assemblies all the way up to system integration. So if you guys have this custom application trying to develop a new laser system for this the surfacing, we can we really like if you kind of come in at the beginning level, because it can really help us really integrate our technology kind of for your maximum benefit, all the way up to kind of the housing system level. And what we're looking for in EPIC here and just in general is to really work with our technology and find these key partners that can utilize our technology and work with them to really develop different applications. What we do in-house is engineering, so utilizing our technology and our expertise to do these high precision optical assemblies and solutions. Analysis of those systems, so we can do FEA, we do a lot of environmental testing, thermal vibration shock, and we do the fabrication. We have the optical shop, assembly, coding, clean room, everything you need to really bring that solution and make it. That's our proprietary know-how. So in regards to this topic, if we can look at some of these sorts of systems. So for surface structuring, you want to basically deliver the beam, and you want to have some, different benefits of the system. So some of the things we could use that are kind of our main core solutions are all these invariant systems. And I'm going to talk a little bit about the last one the most at kind of the end. But there's pentamirrors, there's these, the LTHR, LTHP that I talked about before. And the most is kind of shown on the bottom right. That is really one of our main core technologies, is monolithic structure. Again, invariant, all these being very robust in terms of vibration and thermal concerns. So with this solution, we can really provide a bunch of different benefits for these laser systems. We can use multiple laser systems. So if you want to switch different beams or use multiple beams, the benefit of the most is that it's pre-aligned. So everything in this kind of sandwich structure on the bottom right can basically be put into the system and is extremely accurate. The overall beam deviation goes to the sub-arc second level. So you can basically put this kind of plug and play optic. You don't have to worry about adjusting everything. And it's very highly stable in thermal and vibration. So if you're worried about, doing high scan speeds, you have high power heat issues, vibration issues, these sort of products are used, a lot of our applications are actually military defense. So these are battlefields kind of condition ready optics. So an example to look at, just to see what something like our optics and our solutions can do in this industry. So for instance, we can look at something example like an articulated arm to deliver the optical beam for a laser. So in this system, maybe you have two laser beams that you're going to either split between, or it could be an interferometry kind of setup where you can basically have different optics. This is just one example. We have a pentamirror, but this can be all different types of optics in that first section. And then we can use basically some of our LTHP basically stacked in this kind of articulating arm setup. And we can do multiple axes. But the benefit of this is this invariant system. Because of this, if there's any kind of slight movement or deviation, there's not these alignment issues that may plague your system. So you should be able to get a much higher accuracy at basically at the beam delivery site. With this, you can move the beam around. You're not moving the workpiece. So you can potentially make a much more compact laser system. If you're basically doing this instead of something like a scan lens system, you can have longer, that you're not necessarily required to have the long working distance. So the system could be much more powerful and compact. And it's not limited as much by power handling issues like fiber systems. So a lot of its benefit too is we can deliver high powered lasers with this. So this just shows you on the left kind of the physical layout. I'm going to play this little animation here on the right. Hopefully you guys can see it. So it just shows basically, taking a system, combining some of our high precision assemblies, and basically be having a very robust system for laser scanning on the surface. And we can do multiple configurations. This is just to kind of give you an idea of, one possible version. So with this system, there's a lot of benefits that PLX can offer using that technology. So because they're front surface mirrors, you have wavelength independence. So if you want a quick switch among different lasers, different laser types, wavelengths, that's perfect. Beam diameter. Usually a lot of our systems are around 1 inch to 2 inch diameter, but we can really customize. We've done a lot of different scales. So you can get a large power density and low divergence. The structural design, our elements are enclosed and like I said, pre-aligned, so you get this accuracy. The beam deviation I talked about and variancy is really important to have that performance, and that also comes with a lot of stability. So a lot of our systems, and I'll talk about it in a second, the most is athermal designs with CT match materials. So anything thermal and a vibration or shock is not going to be an issue in our sorts of systems. So I just want to, so I talked about the most briefly. I just want to show just a little quick video so you can kind of see exactly what I'm talking about. Oops. Go through. Play.
Maybe it's on the other screen, if you have a second screen.
No, it's not going. Okay. Let me just show you this one. So basically, if you take kind of a conventional optical bench setup here, you can kind of really combine these elements. So if you think about this in terms of the surface structuring system, you know, you might have all these different elements that are moving and basically being adjusted. So there's a lot more kind of room for error and inaccuracies, especially if your system is scanning really fast and there's vibration and other factors going on. So this really takes those elements out of play and really puts it into this kind of, if you look at this kind of, we call it a sandwich kind of structure. And this is extremely customizable. So we've done all different types of, this happens to be, you know, example is glass, but we can do other materials, metals, ceramics. We can do different elements. We can do freeform optics. This is just, could be mirrors, beam splitters, anything, lenses, anything you can configure can be put into this technology. And with this, because it's in this one structure, this is very robust. So you might think it's glass, it might not be as strong, but it's completely not the case. So these things have been tested and used in very harsh conditions, vibration shock, and large thermal ranges. So these, you know, might be in something that goes shot up into space, or like I said, or for military applications. So I think in this industry, it would be really a great fit. And all of these different elements of PLX, the monolithic, the retroreflectors, we can do a lot of lightweight optics, and variant optics really come into the system integration level. And that's where you can provide the most benefit for you guys developing these sorts of systems. Just to give you just a quick range, you know, of what we can do scale-wise, wavelength ranges, beam deviation, and just sizing. So if you're talking about, you know, depending on the scale of your system, you know, we've made things very, very small down to, let's say, 2 millimeters. We've also done some opto-MEMS as well in this industry. So, and then things up to offset. So we talked about this, those spacing of the beams. We can go up to, you know, basically meters as well. And environmental, I mentioned the shock, I mentioned the temperature variation. These are just some of the numbers, so you can see what we're talking about in terms of shock, vibration, and in temperature range. Okay. And then this is to show you just all the different versions of some of the things that we can do.
Thank you very much, Michelle. Thanks a lot for your contribution. And I think definitely it's very interesting for this community that the high power is actually your systems can stand the high power. You also have put a lot of weight on the let's say harsh environment application. Maybe this is not for the laser structuring people, but I know, for example, Dietmar is also dealing with these devices that can be brought in of course, different environments. So I guess you give a large, nice overview for everything that can be needed also for other projects, side projects of this audience. So it's very good. So are there questions for Michelle? So if it's not the case, someone? No. Okay, I guess, Michelle, you have also the possibility to have a lot of contacts here. So you heard already. Do you want to maybe comment on some collaboration you would like to have? You thought about some speaker before you?
I think there's, I guess, several that basically, if you're developing laser systems, I think we have a lot of applications for you. And we're very always interested in to partner with you and really come up with new kind of merging technologies together. So just reach out to me and we will figure out a system for you. There's nothing we say no to try to develop using our technology. There's so many applications.
That's very good. Then let's keep all this in mind. And if you don't want to, you cannot talk directly with Michelle, we can always make a connection for you. So Michelle also can come back to us and say, I would really to talk with this guy or with this lady. So this will be our job also afterwards. So now we have to go to fantastic labs. So finally, Gwen, thank you for your patience and for your waiting for your slot now. So yeah, we already see the slides, not in presentation mode, but maybe you're going there. Exactly. So Gwen, there you go. Thanks a lot.
Hi, thank you. Thank you very much. Good afternoon, everybody. And thank you, EPIC, for organizing that amazing meeting. I think that I've taken kind of a list of the presentation I had high interest in, and I counted 7. So there are 7 people I would like to be in touch with. I'll get back to you, Jose and Francesca later.
Very good. We're looking forward.
Okay, all right. So I'm here to talk about what beam shaping can bring to surface texturing. And my name is Gwen, as you did mention, and I'm from Skylabs. And in my first slide, I wanted to show some results we had already in surface texturing. And we did that already in the past, LIPS generation. We are kind of new in surface texturing, but well, we were happy to do this collaboration with Alphanov. And therefore, I will start with just a very quick introduction about Skylabs, because you may not know about us yet. We are a pretty young French company. We were founded 6 years ago. And what we do is based on MPLC for multiplane light conversion. It's a unique way to manipulate light. And over the years, because it's pretty unique and it enables a lot of new things, there were many people trusting us, and we did raise nearly 17 million, among which there was 8 million raised last year. And well, we are very happy we've done that last year, because this year is more complicated. So now let's get to the topic. What Skylabs and what beam shaping can bring to surface texturing? Well, basically, our analysis in Skylabs said that there are 2 main ways to do beam shaping. The first way is to use high-power CW lasers, like 1 micron laser or CO2 laser. And the other way, which was actually more discussed today, is to use femtosecond laser or pulse laser in general. It can be also nanosecond or picosecond. Basically, we work on both. And whenever we design our beam shaper, we always focus on 3 different main aspects of what the beam shaping should bring to the process. The first one is the shaping quality. When we do any kind of shape, it can be freeform, really very complex shape. In any case, we want that shape to be of really high quality. And we managed to reach diffraction limited shaping in all cases, meaning that your optics would be actually limiting the quality of the shaping. And the last point in terms of quality, which I want to insist on, is that we don't only have high quality in terms of intensity profile, we have very high quality in terms of phase profile. It means that in the plano where you have your process, you will have a plano phase. And the huge advantage of that is that you preserve the depth of field. Here is just an example of what we got with a line path, very sharp for surface texturing actually, and with a femtosecond laser. The second point, and it was discussed a lot today, and we have a very high interest in that as well, the big challenge of material processing, but more specifically of surface texturing, is to improve yield. Texturing at a higher speed is very important. And we can bring different things to that specific point. The first one is you need to do your process with the optimal shape. For example, if you do surface texturing with a top-hat line instead of a Gaussian beam, you can increase the yield by a factor of maybe 20. That was proven already in the past with our system. The second thing is that you can also do beam splitting. If you split the beams, then you will definitely increase your yield by the same factor. And the last point I want to mention is because our systems are fully reflective, we manage actually to preserve the pulse duration. meaning that you actually preserve your peak power even for femtosecond lasers. So that is actually quite important as well. So here you have just a quick example of how you can improve the yield with the optimal shaping for example, interference patterning. It was discussed a lot already today. Well, basically you can see, and now I'm thinking about some presentation we've seen before. When you do texturing with interferences with a Gaussian beam, you have that kind of shape. And if you have a nice square top hat, you have that kind of interference pattern at the end, and definitely the yield is better. The last point I want to mention is whenever we design also our beam shaper, we are very focused on having robust processes. If one day we want to have our systems in, I would say, factories in the industry, we have to be compatible with all their constraints. The first constraint to accept and to be compatible with is the setup. So we've proven that we can be compatible with robot for high power, and we've proven that we can be compatible with galvo scanner and f-theta lenses for the pulsed application. The second thing is that we've noticed that for high power system, one of the big challenge in terms of robustness was handling focus shift. So we have already proven that we can reduce focus shift because of the way our system are made, fully reflective and easy to cool down. The last point I want to insist on, and I won't have time to get into details on that, is the stabilization of the beam. It's one of the huge challenge for a robust process with femtosecond lasers, and I guess all of you know that already. What we have done is that we have developed a unique feature, which is called mode cleaning, and it actually enables to stabilize the output shape, whatever the instability you have in your femtosecond laser. So basically, all this, we are always focusing on that, having a very high quality, trying to really look on yield improvement, and always look for robust processes as well. So what can we offer? I will be short on that. As I was mentioning, we focus on high power system on one side, and we also focus on pulsed application on the other side. So basically we have systems for both. And in both cases, we are working on developing new catalog references. So I would be happy to discuss further also with people interested on those references, which are actually faster and cheaper to buy from us. On the other side, we also look on custom development. And if you have very specific needs, don't hesitate to get in touch with us, and we can look at how to meet your exact needs. Now, the last slide. Sorry.
Go ahead. Sorry, I thought that you were finished. Please go ahead.
No, I'm sure it was your question, actually.
No, yes, I'm sure.
What can...
Let's do it like this, like it wasn't planned. Thank you very much, Gwen, for a fantastic presentation. Let's do the epic question. What can you do for them? What can they do for you?
Okay, very good. I'm happy to answer that. So basically, I did prepare it very well. I have a site for that.
Can we click share?
Yeah, so I have to share it again.
Let's all see this beautiful slide, which I interrupted.
Do you have it?
We are almost there, yes. Yes.
Okay, good. So basically, I would say that there are two things we are looking for. We have a kind of DNA of innovation in Skylabs, and we are looking for new challenges. If you have new things you have in mind, shapes or features, please contact us. On the other side, we are looking for large projects, because it's a very good way to I don't know, innovate all together to have some very nice result at the end. And we are looking also for that and for main actors on that. Then basically, if you want to have good processes, you need to be in touch with application lab. If you want to be integrated in factories, you have to be in touch with system integrators. And if you want to fit well with the lasers, who know the best the lasers than the laser manufacturers. So we are also looking for this kind of partners. And at last, we have actually a lot of supply chain challenges, as everybody. And today I want to focus on two things that we are currently looking for. It's custom wedge and prism manufacturers and providers of wavefront analyzers. So I am not the point of contact at Skylabs, but please contact me and I will put you in touch with my colleagues who are looking for that definitely. And I hope that answers your question. Thank you for your time. And now, if you have other questions, I'm happy to answer.
Merci beaucoup, Gwen. I didn't want to interrupt you anymore. Thank you. It was a great presentation. For me, it is clear one thing. Do we know what is the most demanded beam shape from the companies who are doing laser-based structuring? Are they looking, what kind of challenges are they presenting to you? Are they looking for a top hat? Are they looking for a Gaussian? What are they looking for?
Well, the truth is that it depends on what they are looking for, but honestly, quite simple top hats have a good success.
Why don't we do
for
something?
Now we
Why
are
don't
focusing
we
on what kind of top hats?
Let's ask them. Let's ask Tim. Tim knows quite a bit about this team. From Dresden, from Fraunhofer-Institut, this greater and this center. What kind of beam shape are you demanding Santa Claus this Christmas?
That's a good question, Jose. Gwen, I was also about to ask, and I'm happy that Jose connect us this way. So actually, we have some interest in the beam shaping, of course. So top hat is always nice to have, of course, to, for instance, speed up the structuring process. And the second thing is, of course, it was this question arose some time ago in the beginning of the meeting, is about, let's say, diffractive optical element efficiency. So either for multi-beam processing or interference or whatsoever. So maybe with the latter, is there some development in terms of increasing the efficiency of diffractive optical elements in the future?
Right. So first of all, what we do is not it's not similar to DOEs, meaning that they are things in common, meaning the kind of shape we target is the same, but the way we implement it is different. So there are differences on how it looks like at the end. And then, can you say again what were your question exactly?
With the beam splitting?
Improving the efficiency.
Yeah, and the efficiency. Yeah. Exactly.
So improving the efficiency then again, it's not that easy to answer because it depends on the shape you are looking for. So basically, we have some system in which we have very nice efficiency. For example, on splitting, we have done some very nice performances, more than 95% of efficiency. On the other side, when we look for complex top hat with complex setup, this beam stabilization actually costs us energy. So we do stabilize the beam pretty well, but the drawback is that we lose energy. So the efficiency can be between 70 to 80%, depending on the laser quality, actually.
Yeah, so it would be definitely interesting to learn more what you can do.
These guys are fantastic. You know, this collaboration is going to be like made in heaven. Sabrina, in Jena, you have been one of the key companies in beam shaping. Actually, today I have two of the biggest key companies in beam shaping in EPIC, Skylabs and Sphericon. Sabrina, after all this introduction, all these presentations, what is your takeaway? What kind of companies you think you can help from a Sphericon side?
I definitely wrote down a few companies here that I do want to get in touch with. That was all the projects around the laser for surf. They were very interesting to us. And then a few more femtosurf. I think we have been in contact quite a while, but I think we have to clarify again what holds him back from testing it, because we were offering a test element for that as well. Yeah, so there's a lot of good things that I will take away from today.
You are always a great speaker. We didn't have this time to put you today, but
it's all right. I really understood it a bit wrong.
You are awesome. You know how much I like you, Sabrina. I want to hear from Joya. Seiya, you are one of the VIP people in all the online technology meetings. What did you get out of this meeting? You make the best coatings I know from Japan.
Yes, so I'm a little bit chatted with Dietmar from Ramteid. So actually, we have done evaluation for the very precise surface finish technology recently, and I hope, I think, and I believe that it helps to improve the detection of the machine vision from the laser technology. So I'm not sure that. And Gwen recently mentioned what we can do for the IBS coating, but I will check internally and we will be back to you.
Definitely IBS is one of the key challenges. We're going to have an event on high power. Minimizing the laser induced Rescoll is being one of the hot topics, and Francesca is the person who is mapping from Optoman to Altecna to, she knows all of them, so you can coordinate with her. I'm gonna finish with when I started. I'm gonna go to Barcelona. I'm gonna go to Raúl. I'm gonna ask him. We had the chance today to hear from different user cases, from Fagor, from Infineon, from Rescoll, from CIC. What is the biggest takeaway you have taken for Microrelleus, Raúl?
Okay, you mean, Jose, You mean the kind of
opportunities for you today?
Sorry?
Opportunities. What opportunities you have seen for helping these end users?
For me, as we, well, a lot of people that I can see here, I think are the ones that work for our machine suppliers, for our femtosecond laser suppliers. And we work more for final companies that could be in automotive market, for example, or could be in electronic appliance, or a lot of different areas, no? So I think I saw here more suppliers of our suppliers that maybe than possible customers, probably. But it's difficult sometimes because a lot of times I can't imagine what I can do for a company. So it's a company that needs to see what we can offer, and they can think about the services we could offer for them.
For me, when I've been chatting with all of you, I have been at the same time chatting in YouTube, answering emails, and writing notes. I took notes. That's how many things I got to at the same time. These have been my learnings this afternoon. First, I did realize that we do, and thanks for the presentation for Tim. He did a fantastic job on really mapping from nanosecond all the way to femtosecond the key applications, the key materials. We have realized, at least for me, that the laser part is very mature. I think we are there. I don't think there is too much improving the laser, but we have problems with the throughput, and there we need multi-beam and we need fast scanning. And that was great to have the different solutions. I really like the presentation from Highlights, from Danijela, on the way of using the DOEs. I love the presentation from Lars, from Last Scan Technology, that we are really in the right path to helping the companies like Microrelleus, like Forget, going into the large volumes. The challenge also has been a bit on the metrology, because a little bit of different application, different approaches. Ramteid did a fantastic job on setting up their solution, but when I asked the end users what kind of metrology they needed, there was different question, different answer, not really a standard answer from them. And when there is no standard, it's when I actually have a lot of fun. So I think we need to address this with SensorFar and other similar companies to have an event on the metrology for this particular market segment. Beam delivery, the top hat at the end we addressed, the different IBS solutions, there is also one of the key challenges. And for me, this meeting was unique because we had 4 different users talking about what they needed. It was cost, speed, and in the medical, Rescoll also brought the regulations as well. There was a really big learning point for me. I think with this has been a great meeting. I would like to remind all of you that if you have any questions, please send them to jose.pozo@epicdatasoft.com. But most important, if you want to connect with any of the participants today, they are really looking forward to talk to you. So all you have to do is send me an email, jose.pozo@epicdatasoft.com. I will introduce you to all the speakers today. With this, I would like to all of you, but especially the people from the Netherlands, I would like to ask you to spend the rest of King's birthday, the rest of Koningsdag with your family at home. Stay healthy, stay safe, be epic. See you soon. Bye-bye.